Black holes are regions of space-time where gravitational fields become so extraordinarily intense that nothing, not matter, not light, not information, can escape once past a critical boundary called the event horizon. They represent the most extreme manifestation of gravity's power, where Einstein's general theory of relativity predicts space-time curvature becomes so severe that it creates a one-way membrane in the fabric of reality itself. Black holes are not physical objects in the conventional sense, with surfaces made of atoms or molecules, but rather pure gravitational phenomena, distortions in space-time geometry so profound that they trap everything within their gravitational grip. This makes them fundamentally different from stars, planets, or any ordinary astronomical object. A black hole is essentially a region where space-time has been warped beyond the point of no return, creating a cosmic trapdoor from which escape is physically impossible according to the laws of physics as we currently understand them. The event horizon defines the point of no return, calculated from the Schwarzschild radius formula R equals 2gm divided by c squared, where g is Newton's gravitational constant, m is the black hole's mass, and c is the speed of light. This radius marks the distance from the black hole's center at which the escape velocity exactly equals light speed. Closer than this distance, even photons traveling at the universe's ultimate speed limit cannot climb out of the gravitational well. They are inexorably pulled toward the center. For a black hole with mass equal to our Sun, the Schwarzschild radius is approximately 3 kilometers. For a black hole containing 4 million solar masses like the one at the center of our Milky Way galaxy, the radius extends to roughly 12 million kilometers, about 17 times the Sun's physical radius. The event horizon is not a physical barrier or surface, but a mathematical boundary in space-time, yet its consequences are absolute. Cross it, and you can never return, communicate, or affect the outside universe in any way. Black holes are not physical objects with tangible surfaces composed of matter, but rather pure manifestations of gravitational fields, warping space-time to its breaking point. Unlike a star held up by internal pressure from nuclear fusion, or a planet supported by electromagnetic forces between atoms, a black hole has no internal structure resisting gravity's inward pull. The matter that formed the black hole has collapsed beyond any possible support mechanism, compressed past the point where quantum degeneracy pressure of the force that supports white dwarfs and neutron stars can halt the collapse. What remains is not a material object, but a geometric feature of space-time itself, a region where the metric, the mathematical description of distances and times, becomes so distorted that it creates a boundary from which light cannot escape. In this sense, asking what a black hole is made of is like asking what a hole in the ground is made of. The hole isn't made of anything. It's defined by the absence and geometry of what surrounds it. Carl Schwarzschild derived the first exact solution to Einstein's field equations in 1916, just months after Einstein published general relativity, and while Schwarzschild himself was serving on the Russian front during World War I. Einstein's equations describe how matter and energy curve space-time, and how that curvature dictates the motion of matter and light. Schwarzschild found a solution for the simplest possible case, a spherically symmetric, non-rotating, uncharged mass. His solution revealed that if all of an object's mass compressed within a critical radius, now called the Schwarzschild radius, then the space-time geometry would develop an event horizon, creating what we now recognize as a black hole. Remarkably, Schwarzschild completed this groundbreaking calculation while stationed in the trenches, sending his results to Einstein, who presented them to the Prussian Academy of Sciences. Schwarzschild died of an autoimmune disease just months later, never knowing that his solution would become one of the most important predictions in all of physics, describing some of the universe's most extreme and mysterious objects. Black holes were initially called frozen stars and later collapsed stars before John Wheeler popularized the term black hole in 1967, though the concept's development spanned decades of theoretical struggle. Early researchers, including Arthur Eddington and other physicists, rejected the possibility that Schwarzschild's solution described real objects, believing nature would somehow prevent complete gravitational collapse. They thought stars would always find a way to support themselves. The term frozen star arose from the realization that from an external observer's perspective, matter falling toward the event horizon appears to slow down asymptotically, never quite crossing the boundary, appearing frozen in time just outside the horizon due to extreme gravitational time dilation. The phrase collapsed star emerged as physicists like Robert Oppenheimer and Hartland Snyder demonstrated in 1939 that sufficiently massive stellar cores would collapse gravitationally without limit once nuclear fuel exhausted. Wheeler's coining of black hole during a 1967 lecture captured the essence perfectly. Black because no light escapes, hole because things fall in but never come out. The name stuck and entered popular imagination. According to the no-hair theorem, black holes are characterized completely by just three observable properties: mass, angular momentum or spin, and electric charge. Everything else about the matter that formed them is lost. The theorem states that all other information, the chemical composition, whether it formed from ordinary matter or antimatter, the detailed structure of the original star is erased during collapse, radiated away as gravitational waves, or hidden forever behind the event horizon. This means a black hole formed from 1 trillion hydrogen atoms is indistinguishable from one formed from 1 trillion iron atoms if they have the same mass, spin, and charge. The theorem, proven by Werner Israel, Brandon Carter, and others in the 1,960 seconds and 1,970 seconds, implies black holes are remarkably simple objects compared to stars. Despite being the endpoints of gravitational collapse from enormously complex stellar structures, they retain only these three numbers describing their state. The theorem's name comes from the phrase, black holes have no hair, meaning no additional distinguishing features beyond mass, spin, and charge. At the center of every black hole, general relativity predicts a singularity where space-time curvature becomes infinite and density reaches infinity within a single geometric point. This is where all the black hole's mass is concentrated according to classical general relativity, not spread throughout the interior volume, but compressed to literally zero volume and infinite density. At the singularity, the equations of general relativity break down, producing mathematical infinities that signal the theory's failure to describe physics at this extreme limit. Most physicists believe quantum gravity effects are yet to be developed theory combining quantum mechanics and general relativity must become important at the singularity, preventing true infinite density and replacing the classical singularity with some kind of quantum structure. Proposed theories include Planck stars with density at the maximum, Planck density, quantum bounce scenarios where collapsing matter rebounds, or space-time foam at the Planck scale. However, the singularity remains hidden behind the event horizon, making direct observation impossible and leaving its true nature one of physics' deepest mysteries. Nothing can escape from inside the event horizon. Not even light travelling at 300,000 kilometers per second. Because the escape velocity exceeds light speed and relativity, forbids faster-than-light travel. This creates absolute causal disconnection between the black hole's interior and the external universe. Any signal, information, or influence originating inside the horizon cannot reach the outside. The interior is literally removed from the rest of space-time's causal structure. Photons emitted inward inside the horizon continue moving toward the singularity despite traveling at light speed. Even photons emitted radially outward are dragged inexorably inward by space-time's extreme inward curvature. From the perspective of an outside observer, the event horizon appears as a dark sphere, a region from which no light emerges. Matter crossing the horizon disappears from view forever, with the infalling object appearing to freeze at the boundary due to gravitational time dilation, making time appear to stop there when viewed from outside. This one-way nature makes black holes cosmic one-way doors. Enter, and you can never leave, communicate, or send information back to the universe you left behind, making the interior forever unknowable to external observers. Stellar mass black holes, deaths of massive stars. Stellar mass black holes form from the gravitational collapse of massive stars, exceeding approximately 20 to 25 solar masses, when their nuclear fuel exhausts and fusion can no longer generate sufficient pressure to counteract gravity's inward pull. During a star's lifetime, nuclear fusion in its core converts hydrogen to helium, helium to carbon and oxygen, and in the most massive stars continues through successive stages, burning neon, oxygen, and silicon, eventually producing an iron core. Iron represents the end of the fusion road because fusing iron nuclei consumes energy rather than releasing it. No energy source remains to support the star. When the iron core grows to approximately 1.4 solar masses, electron degeneracy pressure that had been supporting it against gravity can no longer hold, and the core collapses catastrophically in less than a second. If the remaining core mass after the supernova explosion exceeds approximately 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, above which even neutron degeneracy pressure cannot support the remnant, the collapse continues, past the neutron star stage, and nothing can halt the gravitational infall. The result is a stellar mass black hole. The supernova explosion that announces a massive star's death ejects the star's outer layers into space at velocities reaching 10,000 to 30,000 kilometers per second, enriching the interstellar medium with heavy elements forged in the star's core and during the explosion itself. The explosion releases approximately 10 to the 46th joules of energy, equivalent to the Sun's total energy output over its entire 10 billion year lifetime, compressed into a few seconds. Most of this energy escapes as neutrinos produced when protons and electrons combine to form neutrons during core collapse. The visible light, despite being spectacularly bright and outshining an entire galaxy for weeks, represents less than 1% of the total energy release. What remains after the explosion is the collapsed core. If this core exceeds 3 solar masses, it becomes a black hole, typically with mass between 5 and 20 solar masses, based on observed stellar mass black holes in binary systems. The exact threshold depends on the star's rotation, composition, and mass loss history, but stellar evolution models indicate most stars above 20 to 25 solar masses will end as black holes rather than neutron stars. Typical stellar black hole masses range from approximately 5 to 20 solar masses, based on measurements of black holes in X-ray binary systems, where a black hole accretes matter from a companion star. The lower limit, around 5 solar masses, reflects the TOV limit for neutron stars below roughly 3 solar masses. Neutron degeneracy pressure can support the compact object, producing a neutron star rather than black hole. The gap between 3 and 5 solar masses appears real in observed populations. Though whether this gap represents genuine physics preventing formation of black holes in this mass range, or selection effects in observations, remains debated. The upper limit, around 20 solar masses for stellar black holes formed through single star evolution, reflects how much mass remains after the massive star has lost substantial mass through stellar winds during its lifetime. Very massive stars, exceeding 100 solar masses, lose enormous amounts of mass via radiation pressure-driven winds, potentially leaving cores that still exceed 20 solar masses, but rarely approaching the original star's mass. Binary evolution can produce heavier stellar black holes through mergers or reduced mass loss in close binary systems. Cygnus X1, discovered in 1964 as one of the brightest X-ray sources in the sky, earned distinction as the first compelling black hole candidate and remains one of the best-studied black holes in the universe, located approximately 6,000 light-years away in the constellation Cygnus. The system consists of a massive blue supergiant star, designated HDE 226868, with mass approximately 20 to 40 solar masses, orbiting an invisible compact companion every 5.6 days. The compact object accretes gas from the supergiant's stellar wind, heating it to millions of degrees and producing intense X-ray emission observable by space-based X-ray telescopes. By measuring the supergiant's orbital motion through Doppler shifts in its spectrum and applying Kepler's laws, astronomers determine the compact companion's mass exceeds 15 solar masses, with modern estimates placing it near 21 solar masses, far above the 3 solar mass TOV limit, making a neutron star impossible. Stephen Hawking famously made a bet in 1974 that Cygnus X1 was not a black hole, conceding defeat in 1990 when evidence became overwhelming. The system demonstrates how binary stellar mass black holes reveal themselves through X-ray emissions from accreting material. V404 Cygni, another X-ray binary in Cygnus, contains a black hole of approximately 9 solar masses paired with a low-mass companion star in a 6.5-day orbit, representing one of the best-studied stellar black holes due to recurring outburst behavior. Unlike Cygnus X1, which accretes steadily from stellar winds, V404 Cygni undergoes transient accretion episodes separated by decades of quiescence. During outbursts, accretion rates spike dramatically as material stored in the accretion disk spirals inward, producing some of the brightest X-ray transients observed. Major outbursts occurred in 1938, 1989, and most recently in June 2015, when the system reached visual magnitude 11, bright enough to observe with small telescopes despite being 8,000 light-years distant. Multi-wavelength observations during the 2015 outburst revealed rapid variability on timescales of seconds, jets of relativistic plasma, and complex accretion disk behavior as material plunged into the black hole. The system's relatively low black hole mass and well-constrained orbital parameters make it crucial for testing models of black hole accretion physics and binary evolution. GW150914, detected on the 14th of September 2015, marked the first direct detection of gravitational waves and the first confirmed observation of a binary black hole merger, opening an entirely new window on the universe. The LIGO interferometers in Louisiana and Washington detected a characteristic chirp signal lasting 1/5 of a second as two black holes of approximately 36 and 29 solar masses spiraled together and merged, forming a single black hole of 62 solar masses and releasing 3 solar masses worth of energy as gravitational waves approximately 10 to the 47th joules, radiated in a fraction of a second, exceeding the luminosity of all stars in the observable universe combined during the brief merger. The detection confirmed Einstein's century-old prediction that accelerating massive objects produce ripples in spacetime propagating at light speed, and revealed that stellar mass black hole binaries exist and merge within the universe's current age. The relatively high masses, particularly the 36 solar mass black hole, surprised many astronomers, as stellar evolution models had predicted stellar black holes rarely exceed 20 solar masses. GW 150914 demonstrated that gravitational wave astronomy can detect black holes that emit no light and are completely invisible to electromagnetic observations. Population estimates suggest approximately 100 million stellar mass black holes reside in the Milky Way galaxy, though the uncertainty ranges from 10 million to 1 billion, depending on assumptions about star formation history, massive star evolution, and the fraction of massive stars that produce black holes versus neutron stars. These estimates derive from stellar evolution models and observe star formation rates integrated over the galaxy's 1-3 billion year history. Stars massive enough to produce black holes are rare. Only about 1 inch 1,000 stars has sufficient mass, but over billions of years, and given the Milky Way's 200 to 400 billion total stars, substantial black hole populations accumulate. Most of these black holes are isolated, having formed from single stars or binary systems where the companion was destroyed or ejected, making them completely invisible since they accrete no matter and emit no radiation. They cruise through the galaxy as dark, compact objects, detectable only through gravitational effects like microlensing if they pass between Earth and a background star, or through dynamical effects if they gravitationally perturb nearby stellar systems. Binary systems, where a stellar mass black hole accretes matter from a companion star, emit detectable X-rays, allowing discovery and study. When the companion star is close enough, its outer layers overflow the Roche lobe, the gravitational boundary, where material becomes more attracted to the compact object than to its own star and streams toward the black hole through an accretion disk. Friction and viscous heating in the disk raise temperatures to millions of Kelvin, producing thermal X-ray emission. The strongest X-ray binaries radiate 10 to the 31st to 10 to the 32nd watts in X-rays, easily detectable by space-based X-ray observatories like Chandra, XMM Newton, and NuSTAR, despite distances of thousands of light-years. Approximately 20 confirmed stellar mass black holes in X-ray binaries have been identified in the Milky Way, with masses measured through orbital dynamics of their companion stars. These systems provide laboratories for studying accretion physics, relativistic jets, and strong field gravity near event horizons. Beyond our galaxy, hundreds of X-ray binaries containing stellar mass black holes have been found in nearby galaxies, particularly in the large and small Magellanic Clouds, where active star formation produces massive stars that evolve into black holes. Intermediate mass black holes, the missing link. Intermediate mass black holes occupy the mass range between stellar mass black holes at 5 to 20 solar masses and supermassive black holes at millions to billions of solar masses, spanning approximately 100 to 100,000 solar masses and representing a crucial missing link in understanding black hole populations and formation mechanisms. These objects fill the gap between stellar remnants produced by individual massive star deaths and the galactic giants that dominate galaxy centers, yet they remain among the most elusive and poorly understood black hole types. Their intermediate mass makes them difficult to detect. They're not as common as stellar mass black holes formed through normal stellar evolution, nor as massive and luminous as supermassive black holes when actively accreting. This mass range poses theoretical challenges because no single straightforward formation pathway clearly explains how nature produces black holes of these intermediate masses in significant numbers. Formation mechanisms for intermediate mass black holes remain uncertain, with several competing theories. One possibility involves runaway stellar collisions in dense star clusters, where repeated mergers build up increasingly massive stellar mass objects that eventually collapse. In the cores of globular clusters, ancient spherical collections containing hundreds of thousands to millions of stars, packed into regions just tens of light years across stellar densities, can reach millions of stars per cubic light year. In such extreme environments, stars collide and merge on relatively short timescales. If one star becomes unusually massive through multiple mergers and sits at the cluster's center where collision rates are highest, it could continue growing through additional collisions until reaching 100 to 1,000 solar masses before finally collapsing into an intermediate mass black hole. This runaway process might have been more common in the early universe, when star clusters were denser and more massive. Another formation pathway involves direct collapse of very massive primordial stars in the early universe, potentially creating intermediate mass seed black holes that later grew into supermassive black holes. In the first billion years after the Big Bang, conditions differed significantly from today. No heavy elements existed yet to help gas, clouds cool and fragment into smaller clumps, and some regions might have accumulated exceptionally large masses of pristine hydrogen and helium gas. Under special conditions with minimal heavy element contamination and strong ultraviolet radiation preventing molecular hydrogen formation, these clouds could collapse directly into supermassive stars with masses 10,000 to 100,000 solar masses. Such stars would be short-lived, lasting perhaps only millions of years before collapsing directly into intermediate mass black holes without going supernova. These primordial black hole seeds could then serve as cores around which supermassive black holes grew through subsequent gas accretion and mergers. Hierarchical mergers of stellar mass black holes over billions of years provide a third formation channel. In dense environments like nuclear star clusters at galaxy centers or the central regions of globular clusters, stellar mass black holes can sink to the center through dynamical friction and mass segregation. Once concentrated centrally, they orbit each other and occasionally merge through gravitational wave radiation, forming more massive black holes. Successive generations of mergers could build up intermediate mass black holes with masses reaching hundreds to thousands of solar masses. This scenario became more plausible after LIGO's detections of merging stellar mass black holes demonstrated that such mergers occur throughout the universe. Computer simulations of dense star cluster evolution show that hierarchical mergers can produce intermediate mass black holes, though the efficiency depends sensitively on cluster properties including stellar density, velocity, dispersion, and retention fraction of black holes. Globular clusters provide prime candidates for hosting intermediate mass black holes. These ancient stellar systems orbit the halos of galaxies, including about 150 known in the Milky Way, with ages typically 10 to 13 billion years. Their cores can reach densities where stars are separated by mere light weeks rather than light years, creating conditions favorable for runaway collisions and hierarchical black hole mergers. Observations of globular clusters show evidence for central mass concentrations, regions where stellar velocities increase toward the center, indicating a massive dark object. While some of this mass could be stellar mass black holes and neutron stars, several clusters show kinematics suggesting single intermediate mass black holes with masses 1,000 to 10,000 solar masses. Confirming these detections requires careful dynamical modeling, accounting for cluster geometry, stellar mass functions, and possible tidal influences from the host galaxy. HLX-1, a hyperluminous X-ray source in the outer regions of galaxy, ESO 243-49, represents one of the most compelling intermediate mass black hole candidates. Discovered in 2004 and studied intensively since, it exhibits X-ray luminosity reaching 10 to the 42nd ergs per second during outbursts, 100 to 1,000 times more powerful than typical stellar mass black hole X-ray binaries and too bright to be. Explained by a stellar mass black hole accreting at sub-Eddington rates. The X-ray spectrum shows characteristic properties expected from accretion onto a black hole, including thermal disk emission peaking in the soft X-ray band and power law hard X-ray tail from Comptonization. By fitting disk models to the spectrum and using the relationship between black hole mass, accretion rate, and spectral shape, researchers estimate the black hole mass at approximately 20,000 solar masses. HLX-1's location far from its host galaxy's center suggests it might be the remnant core of a dwarf galaxy that merged with ESO 243-49, with the intermediate mass black hole surviving as the stripped nucleus. GW 190521, a gravitational wave event detected on the 21st of May 2019, produced a final black hole with mass 142, solar masses firmly in the intermediate mass range, formed through the merger of two black holes with masses 85 and 66 solar masses. This detection carries profound implications because it involved black holes in the predicted pair instability mass gap, a mass range from approximately 50 to 130 solar masses, where black holes theoretically cannot form. Through normal stellar evolution, stars in this mass range should completely disrupt in pair instability supernovae without leaving remnants. The progenitor black hole's masses therefore suggest either alternative formation mechanisms or that our understanding of pair instability supernovae requires revision. GW 190521 demonstrates that intermediate mass black holes exist and can form through mergers, providing crucial evidence for hierarchical merger scenarios. The event also produced a final black hole more massive than typical stellar mass objects, potentially representing a new class of intermediate mass black holes detectable through gravitational waves. Ultraluminous X-ray sources, extremely bright X-ray emitters with luminosities exceeding 10 to the 39th ergs per second found in off-nuclear regions of nearby galaxies, have been proposed as intermediate mass black hole candidates, though alternative explanations involving super-Eddington accretion onto stellar mass black holes remain viable. The brightest ULXs reach luminosities 10 to the 40th to 10 to the 41st ergs per second, seemingly requiring black hole masses hundreds to thousands of solar masses if accretion occurs near the Eddington limit. However, observations reveal that some ULXs contain neutron stars or stellar mass black holes accreting at rates exceeding Eddington limits by factors of 10 to 100, with radiation escaping through funnel-shaped geometries, allowing apparent luminosities to exceed isotropic Eddington limits. Distinguishing between intermediate mass black holes accreting at sub-Eddington rates and stellar mass compact objects accreting super-Eddington requires detailed spectral and timing analysis. Intermediate mass black holes remain crucial for understanding the connection between stellar mass and supermassive populations, potentially explaining how supermassive black holes grew so rapidly in the early universe. Supermassive black holes, galactic monsters. Supermassive black holes containing millions to billions of solar masses reside at the centers of most large galaxies, including our Milky Way, profoundly influencing galaxy evolution through their gravitational effects and energetic feedback, when they actively accrete matter. These cosmic behemoths occupy a mass range extending from approximately 1 million solar masses at the lower end to over 60 billion solar masses for the most massive examples, representing a factor of 60,000 inches mass range. Unlike stellar mass black holes that form from individual massive star deaths, supermassive black holes likely formed through different mechanisms in the early universe and grew over billions of years through gas accretion and mergers with other black holes during galaxy collisions. Their masses are so enormous that their event horizons can span tens of millions of kilometers larger than the orbits of inner planets in our solar system, yet they still represent only a tiny fraction, typically 0.1 to 0.2% of their host galaxy's total stellar mass. Sagittarius A*, our Milky Way galaxy's central black hole with mass 4.3 million solar masses, sits at distance 26,000 light-years from Earth in the direction of the constellation Sagittarius. This black hole was confirmed through decades of painstaking observations tracking individual stars orbiting the invisible central mass. Beginning in the 1990 seconds, astronomers using infrared telescopes at Keck Observatory and the Very Large Telescope monitored positions and velocities of stars in the galactic center, particularly the so-called stars orbiting closest to Sagittarius A*, star S2, with orbital period 16 years and closest approach just 120 astronomical units from the black hole, provided the most convincing evidence. By tracking S2's elliptical orbit over multiple periods and measuring velocities up to 7,700 kilometers per second, 2.5% of light-speed astronomers applied Kepler's laws to precisely determine the central mass at 4.3 million solar masses concentrated in regions smaller than our solar system. This work earned Reinhard Genzel and Andrea Ghez the 2020 Nobel Prize in Physics for discovering the supermassive compact object at the Milky Way's center. M87*, the supermassive black hole residing in the giant elliptical galaxy Messier 87 at distance 55 million light-years in the Virgo galaxy cluster, contains approximately 6.5 billion solar masses, over 1,500 times more massive than Sagittarius A*. This black hole achieved worldwide fame in April 2019 when the Event Horizon Telescope collaboration released the first ever image of a black hole shadow, a circular dark region 42 microarcseconds across, equivalent to observing a grapefruit on the moon from Earth. The image showed the black hole silhouetted against the bright emission from the surrounding accretion disk, with light bent by extreme gravity, creating a bright ring around the shadow larger than the actual event horizon due to gravitational lensing. The shadow's size confirmed M87*'s mass to high precision, while asymmetries in the ring's brightness revealed the disk's rotation direction and provided evidence for the black hole's spin. M87 also launches one of the most powerful relativistic jets observed in the universe, extending over 5,000 light-years from the nucleus, and visible even in amateur telescopes as a luminous spike protruding from the galaxy's core. TONS 618, a hyperluminous quasar at redshift 2.219, corresponding to distance approximately 10.4 billion light-years and look-back time 10.4 billion years, contains an estimated 66 billion solar masses, making it one of the most massive black holes known. This black hole shines with such extraordinary luminosity, approximately 4 times 10 to the 40th watts, or 140 trillion solar luminosities, that it outshines its entire host galaxy and can be observed across cosmological distances despite the enormous intervening space. The luminosity derives from gas accreting onto the black hole at rates approaching or exceeding the Eddington limit, converting gravitational potential energy to radiation with approximately 10% efficiency. At this extreme luminosity, TON 618's radiation output equals that of 140 trillion suns combined, making it visible in moderate-sized telescopes despite being among the most distant quasars known. The black hole's enormous mass poses theoretical challenges growing from plausible seed masses of 100,000 solar masses to 66 billion solar masses in the available time since the Big Bang requires sustained accretion at near Eddington rates for over 1 billion years, or formation from much more massive seeds, or episodes of super Eddington accretion exceeding standard theoretical limits. Phoenix A*, located at the center of the Phoenix Galaxy cluster at redshift 0.596, corresponding to distance 5.8 billion light-years, may contain approximately 100 billion solar masses based on mass estimates from X-ray observations, gravitational lensing, and the M-sigma relation, though uncertainties remain large with factor of 2 or factor of 3 uncertainty in the mass. If confirmed, Phoenix A times would be the most massive, supermassive black hole ever discovered. The black hole powers relativistic jets, extending 2.1 million light-years, the longest jets directly traced to a single black hole, inflating giant radio lobes in the surrounding intracluster medium and depositing enormous energy that prevents gas cooling and regulates star formation across the entire massive galaxy cluster. The existence of such ultramassive black holes challenges theoretical models of black hole formation and growth, requiring either exceptionally efficient accretion over cosmic time, formation from extremely massive seed black holes in the early universe, or hierarchical assembly through multiple major mergers of already massive black holes. These supermassive black holes co-evolved with their host galaxies through intimate connection revealed by the M-sigma relation, an empirical correlation discovered in 2000 showing that black hole mass scales with galaxy bulge velocity dispersion as MBH approximately equals 10 to the 8.1 solar masses times quantity sigma divided by 200 kilometers per second to the 4.4 power. Velocity dispersion measures the average random velocities of stars in the galaxy bulge, reflecting the depth of the gravitational potential well, and thus the total mass in stars and dark matter. The tight correlation with scatter only 0.3 to 0.5 dex demonstrates that black hole growth and galaxy evolution are fundamentally coupled rather than occurring independently. The physical origin of this correlation likely involves feedback mechanisms where energy released during black hole growth regulates star formation, preventing galaxies from converting too much gas into stars. During galaxy mergers, gas flows toward the center, fueling both intense starbursts and rapid black hole accretion. As the black hole grows and luminosity increases, radiation pressure and powerful winds heat or expel remaining gas, quenching both star formation and black hole growth in a self-regulating feedback cycle. Formation mechanisms for supermassive black holes remain actively debated, with observational constraints from high redshift quasars requiring seeds to form early and grow rapidly. One leading scenario involves direct collapse of massive primordial gas clouds in the first billion years after the Big Bang, before significant heavy element enrichment. In special environments with strong ultraviolet radiation suppressing molecular hydrogen formation and preventing gas fragmentation into stars, gas clouds of 10,000 to 100,000 solar masses could collapse directly into intermediate mass black hole seeds without forming stars first. Alternative scenarios involve runaway mergers of massive stars in dense protoclusters, producing stellar mass black holes that then grow through accretion and mergers, or population 3 stars, the first generation of stars formed from pristine primordial gas, leaving behind more massive black hole remnants than expected from standard stellar evolution. Regardless of formation mechanism, the seeds must grow through billions of years of gas accretion and mergers with other black holes during hierarchical galaxy assembly, requiring sustained accretion rates approaching the Eddington limit to reach observed masses of billions of solar masses by cosmic ages corresponding to redshift 6 to 7, just 1 billion years after the Big Bang. Active galactic nuclei occur when supermassive black holes accrete substantial amounts of gas, producing luminosities that can outshine the combined light of all stars in their host galaxies by factors of 100 to 1000. The accretion process converts gravitational potential energy into radiation with efficiency approximately 10% for rapidly spinning black holes, far exceeding the 0.7% efficiency of nuclear fusion in stars. AGN display enormous range of observational properties, including safe at galaxies with bright nuclei visible in optical light, radio galaxies with powerful jets extending millions of light years, blazars with jets pointed directly toward Earth producing variable gamma-ray emission, and quasars representing the most luminous AGN. This diversity likely reflects different viewing angles, accretion rates, black hole spins, and host galaxy properties rather than fundamentally different object types. Unified AGN models propose that orientation effects and obscuration by dusty material surrounding the black hole account for much of the observed variety. Looking down on the disk shows broad emission lines from fast-moving gas near the black hole, while edge-on views are obscured by thick dust tori, showing only narrow emission lines from more distant gas. Quasars represent the most luminous subclass of active galactic nuclei, with bolometric luminosities reaching 10 to the 47th ergs per second, equivalent to 1 quadrillion solar luminosities, or 10,000 times the total luminosity of the Milky Way galaxy, concentrated in a region smaller, our solar system. These extraordinary luminosities derive from accretion onto supermassive black holes, with masses typically 1 billion to 10 billion solar masses accreting near the Eddington limit. Quasars are most common at redshifts 2 to 3, corresponding to cosmic ages 2 to 3 billion years after the Big Bang, when gas supplies were abundant and galaxy merger rates were high, providing copious fuel for black hole accretion. The quasar epoch represents a phase when many supermassive black holes experienced their most rapid growth. As the universe aged, and galaxies consumed or expelled their gas supplies through star formation and AGN feedback, quasar activity declined dramatically. Today, most supermassive black holes, including Sagittarius A times, are quiescent or only weakly active, having exhausted their fuel supplies and settling into dormancy, broken only occasionally by tidal disruption events or minor accretion episodes when gas clouds or stars venture too close. The intimate connection between supermassive black hole mass and host galaxy properties extends beyond the M-sigma relation to include correlations with bulge mass, total stellar mass, and even dark matter halo mass in some studies. These correlations demonstrate that black hole growth and galaxy evolution are intimately linked through cosmic history, despite black holes being millions of times smaller than their host galaxies and containing only 0.1 to 0.2% of the total stellar mass. This tiny mass fraction belies the enormous influence black holes exert on galaxy evolution through AGN feedback energy and momentum, injection from accretion and jets heating gas, driving winds, and regulating when and where stars form. Modern cosmological simulations of galaxy formation find that including AGN feedback is essential for reproducing observed galaxy properties, including the galaxy luminosity function, color magnitude relation, and quenching of star formation in massive galaxies. Without AGN feedback, simulations produce too many bright galaxies with excessive star formation that never quenches, failing to match observations. The coevolution of supermassive black holes and galaxies represents one of the most important and still incompletely understood aspects of cosmic structure formation, detecting the invisible finding black holes. Black holes reveal their presence through gravitational effects on surrounding matter and radiation emitted by material falling toward them. Despite the black holes themselves emitting no light and being fundamentally invisible due to their event horizons, preventing escape of any signals from within. Detecting these invisible objects requires indirect methods exploiting their powerful gravity, the characteristic signatures of accretion physics, and the space-time distortions they create. Over the past 60 years, astronomers have developed multiple complementary techniques spanning the electromagnetic spectrum, from radio through optical to X-rays and gamma rays, plus entirely new detection methods using gravitational waves and neutrinos. Each technique provides unique information about black hole properties, including mass, spin, accretion rate, and environmental conditions, while different methods probe different black hole populations, from stellar mass remnants in binary systems to supermassive giants in distant galaxies. X-ray binaries reveal stellar mass black holes through intense X-ray emission produced as companion stars feed matter into hot accretion disks reaching temperatures of millions of degrees Kelvin. When a stellar mass black hole orbits a normal star in a close binary system with orbital periods ranging from hours to days, the black hole's gravity can pull gas from the companion star's outer layers, particularly when the companion evolves into a red giant or supergiant with loosely bound outer atmosphere. The gas doesn't fall directly into the black hole, but instead forms an accretion disk due to conservation of angular momentum. Viscous friction within the disk heats the gas to temperatures where thermal emission peaks in X-rays, typically 10 million Kelvin, producing photons with energies around 1 kilo-electron-volt. The brightest X-ray binaries emit 10 to the 31st to 10 to the 38th ergs per second in X-rays, making them easily detectable by space-based X-ray telescopes like Chandra, XMM Newton, and NuSTAR, despite being thousands of light-years away. The X-ray emission shows rapid variability on timescales from milliseconds to hours, reflecting dynamic processes in the inner accretion disk, where material orbits at substantial fractions of light speed just outside the event horizon. Approximately 20 confirmed stellar mass black holes have been identified in X-ray binaries within the Milky Way through X-ray observations combined with optical spectroscopy measuring companion star orbital motions. Stellar orbital dynamics provide the most direct method for measuring black hole masses by monitoring stars orbiting the invisible gravitating mass and applying Kepler's laws relating orbital period, semi-major axis, and enclosed mass. The technique achieved spectacular success for Sagittarius A*, where infrared telescopes tracked individual stars orbiting the galactic center over decades. Star S2, with 16-year orbital period and highly elliptical orbit, bringing it within 120 astronomical units of the black hole at closest approach, moves at velocities up to 7,700 kilometers per second, 2.5% of light speed. By measuring S2's position and velocity at hundreds of epochs throughout multiple complete orbits, astronomers determined the central mass at 4.3 million solar masses with precision better than 10%. concentrated in a region smaller than 1 astronomical unit, based on the closest approach of S2 and other stars. The observations revealed Keplerian orbital motion precisely following the predictions of Newtonian gravity, plus relativistic corrections from general relativity, including gravitational redshift of starlight measured spectroscopically during close passages, providing the first detection of general relativistic effects in the weak field around Sagittarius A*. Gravitational lensing exploits how black hole gravity bends light following curved spacetime geodesics, creating distorted images, magnification, and multiple images of background sources aligned behind the black hole from our perspective. Strong gravitational lensing occurs when light deflection angles exceed arc-second scales, producing dramatic effects like Einstein rings complete or partial circles of light, when source, lens, and observer align perfectly, and giant luminous arcs stretching tens of arc-seconds across the sky from highly magnified and distorted background galaxies. The lensing mass can be reconstructed from the detailed geometry of lensed images, their positions, shapes, and brightness distributions. For stellar mass black holes, gravitational microlensing produces transient brightening when a black hole passes between Earth and a background star. The black hole's gravity temporarily magnifies the star's light, creating characteristic symmetric light curve rising and falling over days to months, depending on the black hole's mass, velocity, and distance. Several microlensing surveys have detected events consistent with stellar mass black holes. Though distinguishing black holes from neutron stars and other compact objects requires additional information, like measuring the lens mass through astrometric microlensing, detecting the apparent position shift of the background star as gravitational deflection varies during the lensing event. LIGO and Virgo detect gravitational waves from merging black hole binaries through the characteristic chirp signals produced during the final seconds of inspiral, followed by merger and ringdown. The gravitational wave detectors use laser interferometry, measuring tiny changes in the separation between mirrors, separated by 4 kilometers, LIGO, or 3 kilometers, Virgo, with sensitivity reaching strains around 10 to the minus 23rd, detecting changes smaller than 1,000th the diameter of a proton. When gravitational waves from merging black holes pass through the detectors, they alternately stretch and compress space in perpendicular directions at the wave's frequency, modulating the interference pattern of laser beams bouncing between mirrors. The first detection, GW150914 on the 14th of September 2015, showed characteristic frequency increase from 35 Hz to 250 Hz over 0.2 seconds as two black holes with masses 36 and 29 solar masses spiraled together at increasing orbital velocities, merged violently, and produced a 62 solar mass final black hole radiating 3 solar masses worth of energy as gravitational waves. The chirp signal's detailed shape encoded the masses, spins, and distance of the merging black holes, while comparing arrival times at different detectors triangulated the source location in the sky. LIGO and Virgo have now detected approximately 90 gravitational wave events, predominantly binary black hole mergers, revealing a population of black holes spanning masses from 5 to 150 solar masses and merger rates around 50 per cubic gigaparsec per year. The Event Horizon Telescope achieved radio interferometry imaging of M87** shadow by combining 8 radio telescopes across the globe into an Earth-sized virtual telescope with angular resolution 20 micro-arcseconds, sufficient to resolve features at the event horizon scale for nearby supermassive black holes. The telescopes observed M87 simultaneously at wavelength 1.3 mm frequency, 230 GHz, in April 2017, recording petabytes of raw data on hard drives shipped to correlator centers, where specialized supercomputers combined the signals. The technique of very long baseline interferometry achieves angular resolution equal to wavelength divided by maximum telescope separation for 1.3 mm wavelength and Earth diameter baseline 10,000 kilometers. Resolution reaches approximately 20 micro-arc seconds. The resulting image released in April 2019 showed a bright asymmetric ring of emission approximately 42 micro-arc seconds in diameter, surrounding a dark central region, the black hole's shadow cast against the glowing accretion disk. The shadow appears larger than the actual event horizon due to gravitational lensing bending light rays, with photons orbiting close to the photon sphere at 1.5 times Schwarzschild radius before escaping. The ring's brightness asymmetry reveals the accretion disk's rotation direction, with approaching material Doppler boosted to higher brightness than receding material. The shadow's size and shape provided independent confirmation of M87* mass at 6.5 billion solar masses, and consistency with predictions of general relativity for a Kerr black hole. Tidal disruption events occur when stars wander too close to supermassive black holes, approaching within the tidal radius, where differential gravity across the star exceeds its self-gravity, holding it together, causing the star to be torn apart by tidal forces, stretching it into a long, thin stream of stellar debris. The tidal radius, RT, equals approximately stellar radius times cube root of black hole mass, divided by stellar mass, typically around 1 astronomical unit for solar mass star, near million solar mass black hole. Roughly half the stellar debris remains bound and falls back toward the black hole over months to years, forming an accretion disk and producing bright flare as the debris heats through viscous friction to temperatures 10,000 to 100,000 Kelvin. Peak optical and ultraviolet luminosities reach 10 to the 44th to 10 to the 45th ergs per second, comparable to entire galaxy luminosity concentrated in the nucleus, with characteristic rise time weeks and exponential decay. Over months following approximately light curve proportional to time to the -5/3 power predicted theoretically. Observations of TDE light curves and spectra constrain black hole masses typically within factor of few and reveal extreme conditions near the event horizon, including super Eddington accretion rates exceeding standard limits and occasionally relativistic jet launching producing radio and gamma ray emission. TDEs occur at rates approximately 10 to the -4th per galaxy per year, rare but detectable in large surveys monitoring millions of galaxies. Radio observations reveal jets from active black holes emitting synchrotron radiation produced by relativistic electrons spiraling in magnetic fields at velocities approaching light speed. The jets launch perpendicular to accretion disks from regions within tens of gravitational radii of the event horizon, remaining collimated across distances from parsecs to megaparsecs, maintaining narrow opening angles less than 5 degrees over 6 orders of magnitude in scale. Radio emission at frequencies 100 MHz to 100 GHz traces the jet structure with radio spectral index, the slope of flux versus frequency revealing electron energy distributions. Powerful radio galaxies show double-lobed structures where jets terminate in giant bubbles of radio-emitting plasma, extending millions of light-years from the nucleus. Very long baseline interferometry at radio wavelengths achieves milliarc-second angular resolution, resolving jet structures down to parsec scales and revealing details of jet launching, collimation, and internal structure, including knots of emission from shocks and turbulence. Radio jets are observed from both stellar mass black holes in microquasars, showing jets on scales of light days to light years, and supermassive black holes in active galaxies, showing jets extending megaparsecs, demonstrating that jet launching is a universal phenomenon across black hole masses when conditions of rapid spin and strong magnetic fields are met. Reverberation mapping measures time delays between accretion discontinuum emission variations and responses in broad emission lines from surrounding gas clouds, constraining black hole mass and geometry of the broadline region. The technique exploits the fact that emission lines respond to continuum flux changes with time lag equal to light travel time from the disk to the emitting gas. By monitoring AGN spectroscopically over months to years, measuring continuum variability at wavelengths like 5,100 angstroms and emission line responses in lines like H beta at 4,861 angstroms, the time delay tau is measured through cross-correlation analysis. Combined with emission line velocity widths reflecting orbital velocities in the gravitational potential, the virial theorem gives black hole mass as m approximately equals r times v squared divided by g, where r is broadline region radius from c times tau and v is gas velocity from line width. Reverberation mapping has measured black hole masses for over 100 AGN with typical uncertainties 30 to 50%, revealing broadline region radii scale with continuum luminosity following approximately r proportional to L to the 0.5 power to the radius luminosity relation. The technique works for black holes with masses 10 to the 6th to 10 to the 9th solar masses, where broadline region light crossing times range from days to years, accessible to ground-based monitoring campaigns. These complementary detection techniques confirm black holes across the full mass spectrum, from stellar mass remnants of 5 to 150 solar masses revealed through X-ray binaries and gravitational waves, to intermediate mass black holes of 100 to 100,000 solar masses detected through ultraluminous X-ray sources and gravitational wave events, to supermassive black holes of millions to billions of solar masses discovered through stellar dynamics, AGN observations, and direct imaging. The convergence of multiple independent methods measuring consistent properties for the same objects, for instance, M87* mass, determined from stellar dynamics, gas dynamics, jet power, and event horizon telescope shadow size, all agreeing within uncertainties, provides compelling evidence that black holes are real astrophysical objects rather than theoretical curiosities. Modern black hole astronomy combines observations across the full electromagnetic spectrum plus gravitational waves, creating complete picture of black hole populations, their properties, their environments, and their role in cosmic structure evolution from the first galaxies to the present day. Accretion disks, the glowing halos. Accretion disks form from gas and dust spiraling inward toward black holes, converting gravitational potential energy into radiation through viscous friction and compression, transforming otherwise completely invisible black holes into some of the brightest objects in the universe, capable of outshining entire galaxies containing hundreds of billions of stars. The fundamental physics involves conservation of angular momentum. Gas falling toward a black hole cannot plunge straight inward because it possesses angular momentum from its orbital motion around the black hole. This angular momentum must be transported outward before gas can spiral inward, accomplished through viscous torques in the disk where fast-moving inner regions drag slower outer regions forward, transferring angular momentum outward while allowing mass to flow inward. The viscous friction dissipates orbital kinetic energy as heat, raising temperatures to millions of degrees in the inner disk, where the gravitational potential well is deepest, and orbital velocities approach significant fractions of light speed. This makes accretion onto black holes incredibly luminous, converting approximately 10% of infalling rest mass to radiation for rapidly spinning black holes, compared to nuclear fusion's 0.7% efficiency, making accretion the most efficient continuous energy generation process known in the universe after matter-antimatter annihilation. Material falls inward through viscous dissipation following complex fluid dynamics governed by the interplay of gravity, pressure gradients, magnetic fields, and radiation pressure. The viscosity that transports angular momentum outward arises not from molecular collisions, negligible in the tenuous ionized gas of accretion disks, but from turbulent eddies generated by magnetorotational instability, a magnetohydrodynamic instability discovered by Balbus and Hawley in 1991 that fundamentally changed our understanding of accretion physics. The MRI operates in any differentially rotating magnetized plasma, destabilizing even weak magnetic fields and generating turbulent cascade of magnetic fluctuations across scales, from the disk thickness down to microscopic dissipation scales. The turbulence creates effective viscosity parameterized by the Shakura-Sunyaev alpha parameter, typically 0.01 to 0.1, quantifying the ratio of viscous stress to pressure. This turbulent viscosity drives accretion at rates reaching solar masses per year for the most luminous quasars, sufficient to grow supermassive black holes from seed masses of 100,000 solar masses to billions of solar masses over cosmic time. Temperatures range from thousands of Kelvin in outer disk regions, extending to thousands of Schwarzschild radii, where gas first begins its inward spiral after losing angular momentum through viscous torques or magnetic braking, to millions and tens of millions of Kelvin near the inner edge at the innermost stable circular orbit where gas makes its final plunge into the black hole. The temperature profile follows approximately T proportional to R to the -3/4 power for standard geometrically thin, optically thick accretion disks in the Shakura-Sunyaev model, with the power law reflecting energy conservation. Gravitational binding energy released locally must equal energy radiated minus energy advected inward with the flow. For stellar mass black holes with typical masses 10 solar masses and Schwarzschild radius 30 kilometers, inner disk temperatures at the innermost stable orbit, located at 3 times Schwarzschild radius 90 kilometers, for non-rotating black holes reach approximately 10 million Kelvin. For supermassive black holes with masses billions of solar masses, the larger Schwarzschild radii and lower accretion rates per unit black hole mass produce lower inner disk temperatures around 100,000 to 1 million Kelvin, still hot enough to emit copious ultraviolet and soft X-ray radiation. The multi-temperature thermal emission produces continuum spectra spanning infrared through optical, ultraviolet, and into X-rays, with the integrated spectrum appearing as a superposition of black bodies at different temperatures from different disk radii. The hottest inner disk regions dominate emission at shortest wavelengths: X-rays for stellar mass black holes, ultraviolet for supermassive black holes, while progressively cooler outer regions contribute at longer wavelengths. Wien's displacement law relates peak wavelength to temperature through lambda max equals 2.9 millimeters Kelvin divided by temperature, so 10 million Kelvin plasma emits with peak around 3 angstroms soft X-rays. while 100,000 Kelvin plasma peaks near 300 angstroms, extreme ultraviolet. The emergent spectrum from summing all disk annuli produces characteristic shape, Rayleigh-Jean's power law F nu, proportional to nu squared at low frequencies, where disk is optically thick, flattening to approximately F nu, proportional to nu to the 1/3 at intermediate frequencies from geometrically thin disk with temperature gradient, and exponential cutoff at high frequencies where thermal emission from hottest inner disk terminates. Observations of this big blue bump in AGN spectra, from optical through ultraviolet, confirm thermal disk emission and allow constraining inner disk temperature, accretion rate, black hole mass, and spin through spectral fitting. Inner disk regions emit the highest energy radiation due to achieving the highest temperatures from releasing the most gravitational binding energy per unit mass. For stellar mass black holes accreting at modest rates around 0.01 to 0.1 times the Eddington limit, inner disk temperatures reach 1 to 10 million Kelvin, producing thermal X-rays peaking at photon energies around 1 kiloelectron-volt wavelength, 12 angstroms, observable by X-ray satellites. The X-ray flux and spectral shape vary dramatically with accretion rate, and black holes spin higher. Spin allows closer innermost stable orbits where binding energies and temperatures are higher, producing harder X-ray spectra extending to higher energies. Additionally, a hot corona of plasma with temperatures 100 to 500 million Kelvin resides above the disk, inverse Compton scattering disk photons to create hard X-ray tail extending to hundreds of kiloelectron volts. For supermassive black holes, even though inner disk temperatures are lower due to larger physical scales, the disks still produce copious ultraviolet radiation at wavelengths 1000 to 3000 angstroms and soft X-rays below 2 kiloelectron volts from thermal emission, plus hard X-rays from coronal Comptonization. The Eddington limit L-Ed equals 1.3 times 10 to the 38th ergs per second times black hole mass in solar masses sets the maximum luminosity, where outward radiation pressure on electrons balances inward gravitational force on matter, creating equilibrium beyond which radiation pressure would blow away in falling gas and halt accretion. The limit derives from balancing radiation pressure force cross-section times flux over c against gravitational force, gm times mass per electron over r squared, giving L-Ed equals 4 pi gmm proton c over sigma Thomson, where sigma Thomson is the Thomson scattering cross-section. For 10 solar mass stellar black hole, Eddington luminosity is approximately 10 to the 39th ergs per second. For 1 billion solar mass supermassive black hole, approximately 10 to the 47th ergs per second. Exceeding the Eddington limit requires super Eddington accretion, where either radiation escapes through optically thin funnels along rotation axis, allowing higher average accretion rates, or photons are trapped and advected inward with the flow rather than escaping, reducing radiative efficiency but permitting higher mass inflow rates. Super Eddington accretion is observed in ultraluminous X-ray sources, narrow-line safe at 1 galaxies, and possibly the most luminous quasars, enabling extremely rapid black hole growth, potentially explaining how supermassive black holes reached billions of solar masses within the first billion years after the Big Bang. Jets launch perpendicular to the accretion disk plane through magnetic fields, extracting black hole rotational energy via the Blandford's-Najek mechanism, a magnetohydrodynamic process where frame dragging by the spinning black hole twists magnetic field lines, threading the ergosphere and event horizon, inducing electric currents that generate electromagnetic pointing flux flowing outward along the rotation axis. The Poynting flux carries energy and angular momentum extracted from the black hole's spin, with power scaling as omega horizon squared times b squared times r horizon to the fourth, where omega horizon is the angular velocity at the horizon proportional to black hole spin parameter a, b is magnetic field strength at the horizon, and r horizon is horizon radius. For maximally spinning black hole with a equals 0.998 and field strength 1000 Gauss threading the horizon, Blandford's Najek power can reach 10 to the 45th ergs per second for supermassive black hole, with mass 1 billion solar masses sufficient to power the most luminous radio jets observed. The mechanism converts electromagnetic energy to kinetic energy of outflowing plasma through magnetic reconnection and MHD processes, accelerating matter to bulk Lorentz factors, gamma exceeding 10, corresponding to velocities exceeding 99.5% of light speed, creating the relativistic jets observed from microquasars to blazars spanning 9 orders of magnitude in black hole mass. Iron K-alpha fluorescence at 6.4 kiloelectron volts for neutral or weakly ionized iron, increasing to 6.7 kiloelectron volts for highly ionized iron, reveals extreme gravity near the event horizon through gravitationally broadened, redshifted, and Doppler-shifted emission line profiles that extend from approximately 4 to 7 kiloelectron volts depending on disk inclination, black hole spin, and iron ionization state. Iron atoms in the inner accretion disk are illuminated by hard X-rays from the corona above the disk, causing inner shell ionization followed by fluorescence when outer electrons fill the vacancies, emitting characteristic K-alpha photons. These photons escape the disk and propagate toward Earth, but undergo 3 major relativistic effects. Gravitational redshift from climbing out of the deep gravitational potential near the horizon reduces photon energy by factor approximately 1 plus z equals 1 divided by square root of 1 minus 2 gm over rc squared. Transverse Doppler effect from the disk's orbital motion further redshifts photons by factor gamma, where gamma is the relativistic Lorentz factor, and radial Doppler shifts from gas moving toward blue shifted or away redshifted from us. The resulting line profile is dramatically broadened and asymmetric compared to laboratory iron lines that appear as narrow spikes. The relativistic line extends from red wing around 4 kiloelectron volts from maximally redshifted receding, gas to blue wing around 7 kiloelectron volts from approaching gas, with characteristic double-peaked or skewed shape encoding black hole spin, disk inclination, and inner radius. Fitting theoretical relativistic line models to observed X-ray spectra from XMM Newton, Suzaku, and NuStar determines black hole spin with typical uncertainties 0.05 to 0.1 inches spin parameter, revealing that most observed black holes, both stellar mass and supermassive, have high spins with a greater than 0.9, suggesting formation through coherent accretion rather than random chaotic accretion or multiple mergers that would produce lower average spins. The event horizon point of no return. The event horizon marks the ultimate point of no return in spacetime, where the escape velocity equals light speed, defined mathematically by the Schwarzschild radius. R Schwarzschild equals 2 gm divided by c squared, where g is Newton's gravitational constant, m is the black hole mass, and c is the speed of light. This critical radius represents the surface of no return any object, particle, or photon crossing inward past. This boundary can never escape back to the external universe, no matter how powerful a rocket engine it possesses, or how energetically it tries to climb out of the gravitational well. The physical reason is straightforward from Newtonian intuition, even though the full description requires general relativity. Escape velocity at radius r equals square root of 2 gm over r, and setting this equal to light speed c and solving for r gives r equals 2 gm over c squared. Inside this radius, escape velocity exceeds light speed, and since special relativity forbids anything travelling faster than light, escape becomes impossible. The Schwarzschild radius scales linearly with mass, making calculations simple. For the Sun's mass 2 times 10 to the 30th kilograms, Schwarzschild radius is approximately 3 kilometers. For Earth's mass 6 times 10 to the 24th kilograms, approximately 9 millimeters. For a 10 solar mass stellar black hole, approximately 30 kilometers. For Sagittarius A times, with 4.3 million solar masses, approximately 12.7 million kilometers, or 0.085 astronomical units. For M, 87 times, with 6.5 billion solar masses, approximately 19 billion kilometers, or 128 astronomical units. For a 10 solar mass stellar black hole, the Schwarzschild radius is approximately 30 kilometers smaller than most cities on Earth. Compact enough to fit inside a small asteroid. This means the entire mass of 10 suns is compressed within a sphere 60 kilometers in diameter, creating density exceeding nuclear density by many orders of magnitude in the surrounding spacetime curvature. For comparison, a neutron star with mass around 1.4 solar masses and radius approximately 10 to 12 kilometers sits tantalizingly close to its Schwarzschild radius, but doesn't quite cross the threshold neutron degeneracy pressure. Supports the star against complete collapse. If additional mass were added, pushing it above the Tolman-Oppenheimer-Volkoff limit around 2 to 3 solar masses, no known force could prevent collapse through the Schwarzschild radius into a black hole. The 30-kilometer horizon radius seems tiny on astronomical scales, but looms huge compared to the realm where quantum gravity effects become important. The Planck length, 1.6 times 10 to the minus 35th, meters differing by 39 orders of magnitude, meaning classical general relativity remains valid, describing space-time geometry everywhere except possibly at the central singularity. For Sagittarius A times, with mass 4.3 million solar masses, the event horizon extends to approximately 12.7 million kilometers, or roughly 17 times the Sun's radius of 696,000 kilometers. This means the horizon is comparable in size to the orbit of Mercury at 58 million kilometers, though still smaller than Mercury's perihelion. Light takes approximately 42 seconds to travel the horizon's diameter. The horizon's surface area equals 4 pi times radius squared, approximately 2 times 10 to the 15th square kilometers over 1 trillion times Earth's surface area. Despite Sagittarius A asterisks' enormous mass, it appears incredibly small from Earth at distance 26,000 light-years, subtending angular size only 10 micro-arcseconds in the sky, equivalent to seeing a DVD on the moon. This tiny angular size makes direct imaging of Sagittarius A asterisk shadow extraordinarily challenging even for the Event Horizon Telescope, requiring observations at wavelength 1.3 millimeters, where interstellar scattering is minimal and resolution is maximized. The black hole's compactness is staggering. 4.3 million solar masses concentrated in regions smaller than Mercury's orbit represents density vastly exceeding anything achievable in laboratory or even in neutron star cores. The event horizon is a mathematical boundary in space-time rather than a physical surface composed of material. It's a null surface from which outward-directed light rays cannot escape to infinity, defined entirely by the global causal structure of space-time geometry. Unlike the surface of a star or planet, where matter exists with temperature, density, and composition, the horizon is pure geometry with no substance. An infalling observer crossing the horizon encounters no physical barrier, no wall of fire, no discontinuity except in certain quantum gravity scenarios, predicting firewalls that remain controversial. The horizon is not marked by any special local properties. Space-time curvature at the horizon of a supermassive black hole is actually quite mild, with tidal forces at horizon crossing being completely negligible for large enough black holes. The horizon's significance is purely causal and global rather than local. It represents the boundary beyond which causal curves cannot reach spatial infinity, the dividing line between events that can potentially be observed from outside and events forever hidden behind the veil. In this sense, the horizon is more like a point of no return in time rather than a barrier in space, marking the boundary where future directed time-like trajectories unavoidably lead to the singularity. The photon sphere, at 1.5 times the Schwarzschild radius, represents the locus where photons can orbit the black hole in unstable circular trajectories, constantly balanced on the knife edge between falling inward and escaping outward. At this radius, r equals 3 gm over c squared, light rays travelling tangentially neither fall in nor escape, but circle the black hole indefinitely in principle, though any infinitesimal perturbation causes them to either spiral inward or fly outward. The photon sphere is unstable. Unlike planetary orbits, nudge a photon slightly inward and it spirals toward the horizon, nudge slightly outward and it escapes to infinity. For a 10 solar mass black hole, the photon sphere sits at 45 kilometers radius. For Sagittarius A*, approximately 19 million kilometers. The photon sphere is crucial for understanding black hole shadows, observed by the Event Horizon Telescope. Photons approaching the black hole with impact parameters near the photon sphere radius can loop multiple times around the black hole before escaping, creating series of nested bright rings called photon rings stacked around the primary image of the accretion disk. These higher-order images become exponentially dimmer with each additional loop, but in principle, infinite series of progressively fainter rings exists, each encoding information about the black hole's mass and spin through precise angular separations that future instruments might resolve. The innermost stable circular orbit, abbreviated ISCO for non-rotating Schwarzschild black holes, sits at 3 times the Schwarzschild radius, or 6 times gm over c squared, marking the smallest radius at which matter can stably orbit before inevitable plunge into the black hole. Inside ISCO, no stable circular orbits exist. Matter can orbit in unstable circular trajectories between ISCO and photon sphere, but any perturbation causes it to spiral inward. For a 10 solar mass black hole, ISCO is at 90 kilometers radius, with orbital velocity approximately 50% of light speed, and orbital period approximately 0.001 seconds. For rotating Kerr black holes, ISCO location depends strongly on black hole spin parameter A, and whether orbits are prograde aligned with spin or retrograde counter to spin. For maximally rotating black hole with A equals 1, prograde ISCO shrinks to 1 times the horizon radius, while retrograde ISCO expands to 9 times the horizon radius. This dramatic dependence makes ISCO location one of the most important observables for determining black hole spin, since accretion disks extend inward to ISCO and then transition to plunging region where matter falls ballistically. The hot inner edge of the accretion disk at ISCO dominates X-ray emission, so measuring the inner disk radius through X-ray spectroscopy effectively measures ISCO location and hence black hole spin. Crucial distinction exists between the coordinate singularity at the event horizon, a mathematical artifact of Schwarzschild coordinates where metric components diverge, and the physical singularity at the center where space-time curvature truly becomes infinite. Schwarzschild coordinates use time t and radius r as coordinates, but these coordinates become pathological at the horizon. The GTT metric component vanishes while GRR diverges, making it seem like something catastrophic happens at r equals 2 gm over c squared. However, this singularity is purely coordinate dependent, analogous to how spherical coordinates become singular at Earth's poles. Even though nothing special happens there physically, it's just a poor choice of coordinates. Switching to better behaved coordinates like Eddington-Finkelstein coordinates, Kruskal-Siekeres coordinates, or Paine-Levé-Goldstrand coordinates removes the coordinate singularity completely, revealing smooth space-time geometry at the horizon with no local pathology. The physical singularity at r equals 0 is fundamentally different. All coordinate-independent measures of space-time curvature, like the Ricci scalar and Kretschmann scalar, diverge to infinity, indicating genuine breakdown of classical general relativity, where quantum gravity effects must dominate. From the external perspective of distant observers, infalling matter appears to slow down asymptotically and freeze at the horizon due to gravitational time dilation, never quite completing the crossing in finite external time. As an object falls toward the horizon, each successive photon it emits takes longer to reach distant observers because it must climb out of ever deeper gravitational potential. The photons become increasingly redshifted, their energy diminishing as gravitational redshift factor 1 plus z equals 1 divided by square root of 1 minus 2 gm over rc squared approaches infinity as r approaches 2 gm over c squared. The observed time between successive photons increases without bound, making the object appear to slow and freeze just above the horizon. Additionally, the light becomes exponentially dimmer from the combined effects of gravitational redshift reducing photon energy and time dilation reducing photon arrival rate, causing the object's image to fade to invisibility within seconds or minutes, despite theoretically remaining visible forever. An external observer never sees the actual horizon crossing complete. The infalling object's image remains frozen just outside for eternity, though too dim to observe after brief time. From the infalling observer's perspective in their proper reference frame, however, horizon crossing occurs smoothly in finite, proper time, with no local indication of the boundary being crossed and no special physical phenomena marking the event. The infalling observer experiences continuous freefall following a geodesic in curved spacetime. Feeling no forces or stresses, they're in a locally inertial reference frame equivalent to floating freely in deep space, far from gravitational sources, per the equivalence principle. Looking outward as they fall, they see the external universe blue-shifted and time-dilated, with events outside appearing to accelerate. Looking inward toward the singularity, they see normal space-time initially, but as they approach the singularity, tidal forces grow rapidly. For a 10 solar mass stellar black hole, proper time from horizon to singularity is only approximately 10 microseconds for radial infall. For Sagittarius A*, several hours. The infalling observer has no way to determine precisely when they crossed the horizon based on local measurements. They only realize they've crossed when attempting to escape and discovering it's impossible, or when receiving no signals from regions that should be visible if they were still outside. The one-way nature of the event horizon creates absolute causal disconnection between the black hole interior and the external universe. Nothing inside can causally influence anything outside. No signals or information can escape, and the interior is forever hidden from external observations. This causal structure makes the horizon a boundary of no return more absolute than any physical barrier. Even if infalling observers could somehow survive the singularity in a quantum gravity scenario where singularities are resolved, they could never communicate with or return to the external universe. All future directed trajectories inside the horizon lead inevitably towards smaller radius, not back out. The horizon is one-way membrane in space-time, allowing matter and radiation to enter but never exit. From information theoretic perspective, this creates profound puzzle: what happens to information that falls into black holes? Classical general relativity says it's lost forever behind the horizon, but quantum mechanics demands information is conserved through unitary evolution. This information paradox remains one of theoretical physics's deepest unsolved problems, potentially requiring quantum gravity theory for resolution. Crossing the event horizon means embarking on an inevitable journey to the singularity, where tidal forces diverge to infinity and general relativity's equations break down completely, requiring quantum gravity physics that remains undeveloped. Once inside, the radial coordinate r becomes time-like rather than space-like. Decrease in r becomes inevitable passage of time rather than motion through space. Just as we cannot stop time from advancing into the future, an observer inside the horizon cannot prevent r from decreasing towards zero. All future directed paths lead to smaller r, and eventually to r equals zero, where the singularity resides. The singularity is not a place in space, but rather a moment in time that all interior observers inevitably reach. Analogous to the Big Bang singularity, but in reverse. Instead of everything emerging from a singularity in the past, everything inside the horizon converges to a singularity in its future. At the singularity, tidal forces become infinite, the tidal acceleration, scaling as mass over r cubed diverges as r approaches zero, ultimately ripping apart atoms, nuclei, quarks, and possibly space-time itself. General relativity cannot describe physics at the singularity because curvature becomes infinite and equations produce nonsensical infinities. Quantum gravity unifying quantum mechanics and general relativity is required, but remains elusive despite decades of work on string theory, loop quantum gravity, and other approaches attempting to resolve singularities and understand Planck scale physics, where quantum effects on space-time geometry become dominant. Spaghettification, tidal destruction. Spaghettification describes the extreme stretching and compression that objects experience when falling toward black holes due to tidal forces, the differential gravitational pull across an extended body. Gravity weakens with distance, following the inverse square law, so the side of an object closer to the black hole experiences stronger gravitational attraction than the far side. This difference in gravitational force across the object creates tidal stress that stretches the object along the radial direction toward the black hole while compressing it in the perpendicular directions. The term spaghettification captures the visual result. Objects are stretched into long, thin strands resembling spaghetti noodles. For a human falling feet first toward a black hole, the feet experience stronger gravity than the head, pulling the body into an elongated strand while squeezing it narrower from the sides. The strength of this tidal stretching depends on both the black hole's mass and the distance from its center, with smaller black holes producing stronger tidal forces at their event horizons than larger ones. Tidal acceleration, the rate at which tidal forces stretch objects, scales as mass divided by radius cubed, making tidal effects dramatically stronger for smaller black holes at any given distance from the horizon. The mathematical expression for tidal acceleration across an object of length L at distance r from a black hole of mass m is approximately 2 gml divided by r cubed. The inverse cubic dependence on distance means tidal forces increase extremely rapidly as you approach the black hole. But because the Schwarzschild radius itself scales linearly, with mass r equals 2 gm over c squared, the tidal force at the event horizon scales inversely with the square of the black hole's mass. This creates a paradoxical situation where more massive black holes have weaker tidal forces at their event horizons. For a stellar mass black hole of 10 solar masses with Schwarzschild radius 30 kilometers, the tidal acceleration across a 2-meter tall human at the horizon exceeds 1 billion meters per second squared, 100 million times Earth's surface gravity, easily overwhelming molecular bonds and tearing atoms apart. For a supermassive black hole like Sagittarius A times, with 4 million solar masses and Schwarzschild radius 12 million kilometers, tidal acceleration at the horizon is only 0.0001 meters per second squared, 10,000 times weaker than Earth's gravity and completely negligible. For stellar mass black holes, spaghettification begins catastrophically far outside the event horizon, ripping objects to shreds long before they reach the point of no return. A human approaching a 10 solar mass black hole would begin experiencing uncomfortable tidal stretching at distances around 1,000 kilometers, over 30 times the Schwarzschild radius. By the time they reached 300 kilometers, tidal forces would exceed the tensile strength of biological tissue, pulling the body apart. At 100 kilometers, individual cells would be torn apart. At 30 kilometers, right at the event horizon, the tidal acceleration would be so extreme that even atomic nuclei might experience measurable tidal stresses. This means anyone falling into a stellar mass black hole dies from spaghettification long before crossing the event horizon, stretched and compressed into a stream of disassociated atoms. The process would be spectacularly violent and mercifully brief. The time from comfortable to atomized is measured in fractions of a second due to the rapid acceleration toward the black hole. No possible spacecraft or protective technology could resist these tidal forces because they derive from the fundamental geometry of spacetime itself. For supermassive black holes, the situation differs. Dramatically, tidal forces at the event horizon are surprisingly weak, allowing objects and even people to cross the horizon intact, experiencing spaghettification only deep inside as they approach the central singularity. A person could cross Sagittarius A** event horizon at 12 million kilometers, feeling nothing unusual. The tidal acceleration there is less than 1/10,000th of Earth's gravity. They could float through the event horizon in a perfectly normal state, looking back at the universe through increasingly redshifted light for minutes or hours depending on their trajectory. Only as they fell deeper inside, approaching within 1,000 kilometers of the singularity, would tidal forces begin growing to destructive levels. Eventually, within the final seconds before reaching the singularity at r equals 0, tidal forces would diverge to infinity, tearing apart atoms, subatomic particles, and ultimately the fabric of spacetime itself. This delayed spaghettification means hypothetical explorers could potentially cross supermassive black hole horizons and survive briefly inside, observing the strange interior geometry before inevitable destruction. Tidal disruption events occur when stars wander too close to supermassive black holes, approaching within the tidal radius, where tidal forces exceed the star's self-gravity, holding it together. The tidal radius RT equals approximately R star times the cube root of MBH over M star, where R star and M star are the star's radius and mass, and MBH is the black hole mass. For a Sun-like star near a million solar mass black hole, the tidal radius is roughly 1 astronomical unit, 150 million kilometers, or about the Earth-Sun distance. When a star crosses this radius, tidal forces overcome stellar gravity, and the star stretches along the radial direction while compressing perpendicular to it. The differential forces pull the star apart into a long, thin stream of stellar plasma. The leading edge of this stream, moving fastest, continues onward and may escape the black hole entirely, while the trailing edge, moving slower, falls back toward the black hole. Roughly half the stellar mass escapes and half returns, creating a massive accretion event. The fallback accretion from a tidal disruption event produces an extremely bright flare lasting months to years, making TDEs detectable across cosmological distances despite being relatively rare. As the returning stellar debris spirals inward, it forms an accretion disk and heats through friction to millions of degrees. The accretion rate initially far exceeds the Eddington limit, the maximum rate at which a black hole can accrete before radiation pressure halts infall because the debris rains down so rapidly. This super Eddington accretion produces peak luminosities reaching 10 to the 44th to 10 to the 45th ergs per second, comparable to an entire galaxy's luminosity concentrated in the galactic nucleus. The UV and optical brightness increases dramatically over days to weeks, reaches maximum, then slowly fades over months as the debris reservoir depletes. Observationally, TDEs show characteristic spectral signatures, including broad emission lines from the accretion disk, blackbody thermal continua with temperatures 10,000 to 100,000 Kelvin, and in some cases, relativistic jets producing radio and gamma-ray emission. Tidal disruption events occur at rates approximately 10 to the -4th per galaxy per year, about one event per 10,000 years per galaxy, making them rare but observable in large galaxy surveys. In surveys monitoring millions of galaxies, dozens of TDEs are detected annually. The rate depends on the density of stars near galactic nuclei, the black hole's mass, and dynamical processes delivering stars into loss cones, trajectories that intersect the tidal radius. More massive black holes have larger tidal radii, potentially increasing disruption rates, but they also have event horizons that can swallow stars whole before tidal disruption occurs. Black holes exceeding about 100 million solar masses have event horizons larger than their tidal radii for Sun-like stars, meaning stars cross the horizon intact without being disrupted. This creates a maximum black hole mass around 100 million solar masses for TDEs of solar-type stars, though more massive stars or compact objects like white dwarfs can still be disrupted by more massive black holes. Observational signatures of TDEs in ultraviolet, optical, and X-rays make them valuable probes of dormant black holes in galaxy centers that would otherwise remain undetected. Most supermassive black holes are quiescent, not actively accreting, and therefore invisible except through their gravitational influence on surrounding stars. TDEs briefly illuminate these sleeping giants, revealing their presence and allowing mass measurements through the event's properties. The rise time, peak luminosity, and decay timescale depend on black hole mass, stellar mass, and impact parameter, how directly the star's trajectory aimed at the black hole. Fitting TDE light curves and spectra to theoretical models constrains black hole mass typically to within a factor of a few. Spectroscopy reveals extreme velocities tens of thousands of kilometers per second from the disrupted stellar debris, and sometimes shows evidence for relativistic jets launched from the accretion disk. TDEs thus serve as natural experiments probing tidal physics, accretion dynamics, jet formation, and black hole demographics, particularly for intermediate mass black holes where other detection methods struggle. The violent drama of stars torn apart by gravity makes TDEs both spectacular demonstrations of tidal forces and valuable astronomical tools. Time dilation, gravity slowing clocks. Gravitational time dilation causes clocks to run slower in stronger gravitational fields. A fundamental prediction of general relativity confirmed by countless experiments. The effect arises because gravity curves space-time, and this curvature affects time's passage. The time dilation factor equals 1 divided by the square root of 1 minus 2 gm over rc squared, where g is gravitational constant, m is mass creating the field, r is distance from that mass, and c is light speed. This factor approaches unity far from gravitational sources, where space-time is nearly flat, but grows larger as gravity strengthens. Near massive compact objects like black holes, time dilation becomes extreme. The formula reveals that as radius r approaches the Schwarzschild radius 2 gm over c squared, the denominator approaches zero, making the time dilation factor approach infinity. This means time appears to stop at the event horizon from the perspective of distant observers, though proper time continues normally for infalling observers crossing the horizon. GPS satellites orbiting Earth at 20,000 kilometers altitude must account for both special and general relativistic time dilation effects to maintain positioning accuracy. Special relativity's time dilation from orbital velocity at 14,000 kilometers per hour causes satellite clocks to run slower by 7 microseconds per day compared to ground clocks. But general relativistic gravitational time dilation has the opposite effect. Weaker gravity at orbital altitude causes satellite clocks to run faster by 45 microseconds per day. The net effect is 38 microseconds per day gain, which without correction would cause positioning errors accumulating at 10 kilometers per day. GPS system designers incorporate relativistic corrections into satellite clock frequencies and positioning algorithms, making GPS a practical everyday application of Einstein's theories. This demonstrates time dilation is not abstract theoretical curiosity, but measurable reality affecting modern technology. Near black holes, time dilation effects become dramatically more severe. At one point, 1 times the Schwarzschild radius just 10% farther than the horizon time passes at roughly 30% the rate of distant clocks. A clock here ticks 3 times for every 10 ticks of a distant clock, meaning 1 hour locally corresponds to over 3 hours for distant observers. At 1.01 times the Schwarzschild radius, time dilation reduces to about 10%. 1 local hour equals 10 distant hours. These extreme time dilation factors create bizarre consequences. An observer hovering just outside a stellar mass black hole's horizon for what seems like 1 hour locally would find that 10 hours passed for distant observers. If they hovered there for a subjective day, over a week would pass outside. Communications with distant observers would be profoundly affected. Messages sent outward would be stretched in time and redshifted in frequency, while incoming messages would appear blue-shifted and time compressed. At the event horizon itself, time dilation becomes infinite. From the external perspective, clocks appear completely frozen. Light redshifts to infinite wavelength, and infalling objects never appear to complete their crossing. An observer watching someone fall toward a black hole would see them approach the horizon asymptotically, slowing down continuously, appearing to freeze in time just above the horizon. The infalling person's image would become increasingly red-shifted, shifting from visible light to infrared to radio waves, dimming exponentially as photons lose energy climbing out of the deepening gravitational well. Theoretically, the image would persist forever, infinitely red-shifted and dim, frozen at the horizon. In practice, the image becomes too dim to detect within seconds or minutes, and quantum effects eventually cause it to fade completely. But mathematically, the information remains encoded on the horizon forever according to holographic principle. However, this infinite time dilation is coordinate effect rather than physical reality. It results from using Schwarzschild coordinates, which become singular at the horizon. Infalling observers experience no infinite time dilation in their own reference frame. From their perspective, crossing the horizon occurs in finite, proper time, with nothing unusual happening locally. For a stellar mass black hole of 10 solar masses, proper time from horizon to singularity is approximately 10 microseconds for radial infall. For Sagittarius A times with 4 million solar masses, proper time from horizon to singularity is several hours. The infalling observer simply falls through the horizon smoothly, continuing inward toward inevitable encounter with the singularity. This represents one of general relativity's most counterintuitive features. Different observers in different reference frames have fundamentally different experiences of the same events, with no objective universal truth about when horizon crossing occurs. Gravitational redshift, Z equals gm over rc squared, quantifies wavelength stretching as photons climb out of gravitational wells. Light emitted from strong gravitational fields loses energy, fighting gravity, increasing wavelength and decreasing frequency. The redshift factor relates observed wavelength to emitted wavelength through the formula 1 plus Z equals observed wavelength over emitted wavelength. For light escaping from near a black hole's horizon, gravitational redshift becomes enormous. At twice the Schwarzschild radius, gravitational redshift is Z, approximately 0.4, meaning light is redshifted by 40%. Blue light emerges as red light. At one point, 1 times Schwarzschild radius, Z, approximately 2, meaning wavelengths triple ultraviolet light, emerges as deep infrared. As emission point approaches the horizon, redshift diverges to infinity. This gravitational redshift has been measured directly in spectral lines from stars orbiting Sagittarius A*. The star S2 orbiting Sagittarius A times with 16-year period provided crucial tests of general relativity's predictions for gravitational redshift and time dilation. At closest approach in 2018, S2 reached 120 astronomical units from the black hole, about 1,400 times the Schwarzschild radius, traveling at approximately 7,700 kilometers per second, or 2.5% light speed. Detailed spectroscopy during this close passage measured combined gravitational redshift and transverse Doppler shift from special relativity. The observations matched general relativity's predictions to within observational uncertainties, confirming Einstein's theory in this strong field regime. Gravitational redshift measurements from S2 and other stars continue improving precision as orbital coverage expands and spectroscopic accuracy increases. Future observations may detect relativistic precession, frame dragging, and other general relativistic effects. These tests demonstrate general relativity works correctly, even in gravitational fields billions of times stronger than Earth's, building confidence in applying the theory to event horizon vicinity where fields are stronger still. Extreme radiation near the horizon. X-ray emission from hot inner accretion disks represents the primary radiation signature from black holes, produced as gravitational potential energy, converts to thermal energy through viscous dissipation. Gas, spiraling inward, reaches temperatures from thousands of Kelvin in outer disk regions to millions and tens of millions of Kelvin near the innermost stable circular orbit. These extreme temperatures follow from the binding energy released material at the ISCO has gravitational binding energy approximately 10% of rest mass for rapidly spinning black holes. As gas spirals inward through the disk, viscous friction converts orbital kinetic energy to heat, with temperature scaling as the fourth root of local energy dissipation rate. For stellar mass black holes with typical masses 10 solar masses, inner disk temperatures reach 10 million Kelvin, producing characteristic thermal emission peaking at X-ray energies around 1 kiloelectron-volt. For supermassive black holes, lower temperatures produce peak emission in ultraviolet, though X-rays are still copiously produced through non-thermal processes in the corona above the disk. Inverse Compton scattering in the corona generates hard X-rays extending to energies exceeding 100 keV. The corona consists of hot plasma with temperatures 100 to 500 million Kelvin residing above and possibly within the accretion disk. Low-energy photons from the cooler disk scatter off hot electrons in the corona, gaining energy through inverse Compton process. Each scattering boosts photon energy by factor approximately 4 kT over electron mass times c squared, where K is Boltzmann constant and T is electron temperature. Multiple scatterings produce power law energy distribution extending to high energies. The resulting X-ray spectrum shows characteristic shape. Thermal disk emission dominates soft X-rays below few keV, while power law Comptonized emission dominates above 10 keV. Observing this spectral transition allows determining coronal temperature and optical depth. NuSTAR and other hard X-ray missions observe this high-energy tail, constraining corona physics and black hole spin through relativistic disk reflection signatures imprinted on the spectrum. Synchrotron radiation from relativistic electrons spiraling in magnetic fields produces emission across electromagnetic spectrum, from radio through optical to X-rays, depending on electron energies and field strengths. In jets and accretion disk coronae, magnetic fields reach 100 to 10,000 Gauss, and particle acceleration mechanisms, like shock waves and magnetic reconnection, boost electrons to Lorentz factors exceeding 1000. These relativistic electrons emit synchrotron photons at frequencies nu approximately gamma squared times EB over 2 pi MEC, where gamma is electron Lorentz factor, E is charge, B is magnetic field, and ME is electron mass. For gamma around 10,000 and B around 100 Gauss, characteristic synchrotron frequency reaches X-ray energies. The synchrotron power law spectrum F nu proportional to nu to the negative alpha, with spectral index alpha approximately 0.7, is observed from radio through X-rays in many black hole systems, revealing non-thermal electron populations. Hawking radiation represents quantum mechanical thermal emission from black hole event horizons, predicted theoretically but never observed due to extraordinarily low temperatures for astrophysical black holes. Stephen Hawking showed in 1974 that quantum field theory in curved spacetime predicts black holes radiate thermally with temperature Th equals h bar cubed over 8 pi GMKB, where h bar is reduced Planck constant and Kb is Boltzmann constant. For stellar mass 10 solar mass black hole, Hawking temperature is approximately 6 nanokelvin, 6 billionths of a degree above absolute zero. This thermal emission is utterly negligible compared to cosmic microwave background temperature 2.7 Kelvin, meaning stellar and supermassive black holes absorb far more CMB radiation than they emit through Hawking radiation. Only microscopic black holes, with masses below approximately 1 billion kilograms, have Hawking temperatures exceeding CMB temperature, allowing net radiation. Black holes smaller than Mount Everest's mass radiate significantly, while those smaller than 10,000 tons glow intensely, approaching final explosive evaporation. Black hole thermodynamics connects black hole mechanics to thermal physics through Bekenstein-Hawking entropy formula S equals Ka over 4 times Planck length squared, where A is horizon area and Planck length equals square root of hg over cubed, approximately 1.6 times 10 to the minus 35th meters. This formula reveals black holes have enormous entropy proportional to horizon area rather than volume. A 10 solar mass black hole has entropy approximately 10 to the 54th times Boltzmann constant, exceeding entropy of the Sun by factor 10 to the 20th. The area law implies information content of space-time regions is bounded by surface area rather than volume, motivating holographic principle. Black hole thermodynamics establishes 4 laws analogous to classical thermodynamics. 0th law relates to constant surface gravity on horizon. First law connects energy changes to area and angular momentum changes. Second law states total black hole area never decreases classically. Third law prevents reaching 0 surface gravity in finite steps. These laws suggest deep connection between gravity, quantum mechanics, and thermodynamics. The information paradox asks whether information falling into black holes is permanently lost or eventually recovered, posing fundamental conflict between quantum mechanics' unitarity and general relativity's predictions. Quantum mechanics requires unitary evolution preserving information. Knowing initial quantum state allows calculating future states uniquely and reversing to determine past states. But general relativity indicates matter crossing event horizon falls irretrievably to singularity, its information lost to outside universe. When black holes evaporate through Hawking radiation, they emit purely thermal radiation carrying no information about specific matter that fell in only total mass, spin, and charge matter. If black hole evaporates completely, information about all matter that ever fell in seems destroyed, violating quantum unitarity. Proposed resolutions include information encoded in subtle correlations in Hawking radiation, requiring quantum gravity calculations, information stored at stretched horizon or in microscopic degrees of freedom, information escaping through baby universe formation, or genuinely non-unitary evolution for black holes modifying quantum mechanics. Recent progress using AD-S CFT correspondence and quantum information theory suggests information is preserved through Hawking radiation correlations, though calculations are incomplete. The correspondence relates quantum gravity in anti-de Sitter spacetime to conformal field theory on boundary, providing concrete realization of holographic principle. In this framework, black hole formation and evaporation is unitary process in boundary CFT, implying information preserves despite appearing to be lost from bulk perspective. Page curve calculations show entropy of Hawking radiation initially increases as radiation escapes, then decreases as quantum entanglement between early and late radiation carries information out, ultimately reaching 0 when black hole evaporates completely. This suggests information is recoverable in principle, though extracting information from Hawking radiation would require detecting impossibly subtle correlations across the radiation. The paradox remains active research area connecting quantum information, quantum gravity, and holography, with implications for fundamental nature of spacetime, information, and reality. Kerr black holes, rotation and spin. Real astrophysical black holes rotate, described by Kerr solution discovered by Roy Kerr in 1963, which generalizes Schwarzschild solution to include angular momentum. While Schwarzschild solution assumes spherical symmetry from non-rotating mass, Kerr solution describes axially symmetric spacetime around spinning black hole. The spin parameter A equals J times C over gm squared, where J is angular momentum, ranging from 0 for non-rotating Schwarzschild black holes to 1 for maximally rotating Kerr black holes spinning at theoretical limit. Most observed black holes have high spins with a greater than 0.9 based on X-ray spectroscopy measurements. Rotation profoundly affects spacetime geometry near black holes, creating ergosphere, altering event horizon shape and size, changing ISCO location, and enabling energy extraction through Penrose process and Blandford-Znajek mechanism. Understanding Kerr black holes is essential because rotation is generic formation through stellar collapse or accretion naturally produces rotating black holes, while non-rotating Schwarzschild black holes represent idealized special case unlikely to occur in nature. Frame dragging, the lens-tharing effect, causes rotating mass to drag spacetime into rotational motion like honey swirling around spinning spoon. Near rapidly rotating black hole, frame dragging becomes so extreme that spacetime itself rotates at velocities approaching light speed. Stationary observers cannot exist in strongly frame-dragged regions. They must orbit black hole, whether they wish to or not, because spacetime beneath them is rotating. The effect grows stronger closer to the horizon and at lower latitudes nearer the equatorial plane. Frame-dragging velocity reaches maximum at the ergosphere boundary, where frame-dragging forces all observers to co-rotate with the black hole. This spacetime rotation twists magnetic field lines, generates electric currents, and enables jet-launching mechanisms, extracting black hole spin energy. Frame dragging has been measured directly in Earth's vicinity using Gravity Probe B satellite, which detected tiny precession of gyroscopes due to Earth's rotation, dragging nearby spacetime, confirming general relativity's predictions at parts per million precision. The ergosphere is the region between outer boundary, where frame dragging becomes absolute, and the event horizon, unique to rotating black holes with no analogue in Schwarzschild geometry. In this region, remaining stationary relative to distant observers becomes impossible. All trajectories must rotate with the black hole. The ergosphere's outer boundary, called the static limit or ergo surface, occurs where time-like killing vector becomes space-like. At radius r equals gm over c squared plus square root of quantity gm over c squared squared minus a squared times cosine squared theta, where theta is polar angle. At equator, where theta equals 90 degrees, ergosphere extends farthest reaching approximately 2 gm over c squared for maximal spin. At poles where theta equals 0 or 180 degrees, ergosphere boundary coincides with event horizon. The name derives from Greek ergon, meaning work, energy, can be extracted from this region through Penrose process, effectively mining black holes' rotational energy, stored in space-time rotation itself. ISCO location depends strongly on spin parameter, ranging from 6 times Schwarzschild radius for non-rotating black holes, down to just 1 times Schwarzschild radius for maximally rotating black holes, with prograde orbits aligned with spin. For retrograde orbits counter to spin direction, ISCO moves outward, reaching 9 times Schwarzschild radius for maximal spin. This dramatic difference in ISCO radius affects accretion disk physics, emission spectra, and energy extraction efficiency. High-spin black holes have accretion disks extending much closer to horizon, where gravitational binding energy and orbital velocities are higher, producing hotter, more luminous emission. The radiative efficiency fraction of rest mass converted to radiation increases from 6% for non-rotating black holes to 42% for maximally rotating black holes, making spin crucial factor determining AGN and quasar luminosities. Measuring ISCO location through X-ray spectroscopy and timing provides most reliable method for determining black hole spin in accreting systems. Measuring black hole spin relies primarily on X-ray observations of ion, K-alpha, emission line, shape, and X-ray continuum, spectrum from accretion disk. The relativistic ion line profile depends sensitively on innermost disk radius, which equals ISCO, determined by spin. High-spin black holes with ISCO at 1 to 2 Schwarzschild radii show broad asymmetric ion lines extending from 3 to 4 keV to 7 to 8 keV, with characteristic red wing from gravitational redshift and blue wing from gravitational redshift, approaching disk material. Low-spin black holes with ISCO at 4 to 6 Schwarzschild radii show narrower lines. Fitting relativistic line models to high-quality X-ray spectra from XMM Newton, NuSTAR, and NICER determines spin with typical uncertainties 0.1 inches spin parameter. Most stellar mass and supermassive black holes observed show high spins are greater than 0.9, suggesting either formation mechanisms preferentially produce high spin or accretion efficiently spins up black holes. Alternative spin measurements use X-ray continuum fitting, quasi-periodic oscillation frequencies, and jet power correlations, providing consistency checks on spectroscopic spin determinations. Charged black holes Reissner-Nordström solution. Charged black holes described by the Reissner-Nordström metric add electric charge Q to mass m as a second parameter beyond the Schwarzschild solution's single mass parameter, creating a fundamentally different space-time geometry where electromagnetic forces compete with gravity. Discovered independently by German physicist Hans Reissner in 1916, the same year as Schwarzschild's solution, and Finnish physicist Gunnar Nordström in 1918. The solution describes spherically symmetric spacetime around an electrically charged, non-rotating point mass. The Reissner-Nordström metric includes electromagnetic contributions to the stress energy tensor on the right-hand side of Einstein's field equations. The charge Q sources electromagnetic fields governed by Maxwell's equations, and these fields carry energy momentum that curves space-time beyond the curvature from mass alone, with charge adding a repulsive electromagnetic force that competes against gravity's attractive pull. The space-time geometry differs qualitatively from Schwarzschild, producing 2 horizons instead of 1 and creating the exotic region between them. The event horizon radius becomes r plus equals gm over c squared plus square root of quantity gm over c squared all squared minus gq squared divided by 4 pi times epsilon naught times c to the 4th, where epsilon naught equals 8.85, 4 times 10 to the minus 12th farads per meter is the vacuum permittivity constant. For small charges where Q approaches 0, the square root approximately equals gm over c squared, and r plus approximately equals 2 gm over c squared, recovering Schwarzschild radius. As charge increases, the square root term decreases, causing horizon radius to shrink. Below Schwarzschild value, electromagnetic repulsion partially counteracts gravity, requiring closer approach before horizon forms. For the extremal case, where q squared exactly equals gm squared divided by epsilon naught g, written more simply in geometric units as q equals m, the square root term vanishes identically, making r plus equals r minus equals gm over c squared. The inner and outer horizons coincide at a single degenerate horizon. This extremal Reisner-Nordström black hole represents a special limiting case of great theoretical interest in quantum gravity, string theory, and studies of black hole thermodynamics. If charge exceeds this extremal value with q squared greater than gm squared over epsilon naught g, no real solutions exist for horizon radii. The square root becomes imaginary, meaning no event horizons form at all. What remains is a naked singularity, a singularity at r equals 0 that is visible and causally connected to the external universe without any horizon to hide it. Such naked singularities violate the cosmic censorship conjecture proposed by Roger Penrose, which asserts that all singularities formed by realistic gravitational collapse must be hidden behind event horizons, preventing the breakdown of predictability that would occur if singularities communicated with the external universe. Most physicists believe nature enforces cosmic censorship through some mechanism that prevents overcharging black holes or discharging them if charge somehow exceeded extremal values. Numerical simulations of charged matter collapse suggest that when in falling charge approaches extremal values, electromagnetic repulsion becomes so strong that collapse halts, mass energy escapes as electromagnetic radiation, and charge dissipates, preventing naked singularity formation. Reisner-Nordström black holes possess inner and outer event horizons at radii r plus and r minus, unlike Schwarzschild black holes, which have only a single horizon, creating a much richer and more complex causal structure with multiple regions having different geometric properties. The outer horizon at r plus equals gm over c squared plus square root of gm over c squared squared minus gq squared over 4 pi epsilon naught c to fourth represents the standard event horizon. Analogous to Schwarzschild, once crossed from outside, escape back to spatial infinity becomes impossible. The inner horizon, called the Cauchy horizon, at radius r minus equals gm over c squared minus square root of gm over c squared squared minus gq squared over 4 pi epsilon naught c to fourth marks the boundary of the region where space-time evolution is determined by initial data specified outside. It represents the boundary of deterministic predictability. Between the outer and inner horizons lies an exotic region where weird physics operates, including peculiar causal structure, intense blue shifting of infalling radiation, and in the rotating charged Kerr-Newman generalization, closed time-like curves trajectories through space-time that loop back in time, allowing time travel in principle, though probably rendered impossible by quantum instabilities. The inner Cauchy horizon is deeply unstable in a fundamental way. Any small perturbation, such as infalling matter or radiation, gets infinitely blue shifted as it approaches the Cauchy horizon from outside, piling up enormous energy density that likely causes the horizon to collapse into a curvature singularity called a mass inflation singularity. This instability, discovered through detailed stability analysis and numerical simulations, likely prevents the Cauchy horizon from existing in realistic black holes, with quantum effects or classical instabilities destroying it and converting the region into a singularity. The inner horizon structure reveals profound limitations of classical general relativity, and suggests quantum gravity effects become essential for describing the complete space-time geometry inside charged or rotating black holes. Classical general relativity predicts the Cauchy horizon as a null surface, but quantum field theory in curved space-time shows vacuum polarization and particle creation effects diverge at the Cauchy horizon, suggesting semi-classical analysis breaks down there. Most theoretical work on charged black holes focuses on extremal and near-extremal cases where inner and outer horizons nearly coincide, as these configurations are relevant for certain quantum gravity calculations, string theory constructions, and applications of the AD-S CFT correspondence. A profound duality relating quantum gravity in anti de Sitter spacetime to conformal field theories on the boundary. Near-extremal Reisner-Nordström black holes in AD space serve as important theoretical laboratories for understanding quantum aspects of black holes, including Hawking radiation, entropy counting from microscopic degrees of freedom, and information paradox resolution. However, these theoretical applications focus on idealized mathematical solutions rather than astrophysically realistic black holes, which are essentially uncharged, as discussed below. Astrophysical black holes are almost certainly electrically uncharged because accreting plasma rapidly neutralizes any net charge through preferential accretion of opposite charge particles, with charge dissipation timescales many orders of magnitude shorter than any astrophysically relevant timescales. Consider a black hole that somehow acquired positive electric charge, perhaps through asymmetric accretion or charge separation in magnetic fields. The positive charge creates an outward-pointing electric field that attracts negatively charged electrons while repelling positively charged protons and ions. In the surrounding plasma ionized gas containing equal numbers of electrons and ions, maintaining quasi-neutrality overall, electrons are preferentially attracted toward the black hole and fall in more readily than ions, carrying negative charge into the black hole. This continues until the black hole's charge neutralizes, with the timescale for neutralization being remarkably short. The charge dissipation timescale is approximately r Schwarzschild times square root of mass over charge expressed in geometric units, working out to microseconds or milliseconds for stellar mass black holes and seconds for supermassive black holes. Accretion timescales are years to millions of years, meaning charge dissipates essentially instantaneously compared to accretion. Even if some process continuously recharged the black hole, the rate of charge input would need to match or exceed the rapid discharge rate, which seems impossible given that accretion disks naturally contain equal charge densities of opposite signs, meaning accreted plasma carries zero net charge on average. A positively charged black hole attracts electrons preferentially over protons due to electromagnetic force scaling with charge, quickly accumulating electrons until charge neutralizes, typically within microseconds to seconds, depending on ambient plasma density and black hole mass. Accretion disks consist of ionized plasma containing electrons and ions in equal numbers. The plasma is electrically neutral overall, with charge density essentially zero, though local fluctuations exist. When this neutral plasma accretes onto a charged black hole, electromagnetic forces cause slight charge separation, with opposite charges attracted preferentially, but the net effect rapidly neutralizes the black hole's charge. Even if the black hole somehow acquired charge through asymmetric accretion or charge separation processes in strong magnetic fields twisting through the disk, electromagnetic repulsion of like charges limits how much charge can accumulate. The maximum voltage a black hole can sustain before electromagnetic breakdown and discharge occurs is approximately 10 to the 19th volts times the mass in solar masses for a 10 solar mass black hole, about 10 to the 20th volts for a billion solar mass supermassive black hole, 10 to the 28th volts. While these voltages sound enormous, in practice the charge-to-mass ratio remains utterly negligible compared to extremal values needed to approach Reissner-Nordström black hole geometry. For a 10 solar mass stellar black hole, the extremal charge, the maximum charge possible while maintaining an event horizon, equals approximately 10 to the 21st coulombs based on q squared equals gm squared over epsilon naught g. For comparison, realistic charges that might accumulate are estimated at less than 10 coulombs based on charge separation mechanisms and plasma physics in accretion flows, meaning actual charge is 20 orders of magnitude smaller than extremal charge. The ratio of electromagnetic to gravitational potential energy is proportional to q squared over gm squared times c to 4th epsilon naught, which for realistic charges versus extremal charge equals approximately 10 to the minus 40th. Electromagnetic effects are utterly negligible compared to gravity. For supermassive black holes with masses billions of solar masses, extremal charge would be 10 to the 30th coulombs, while realistic charges remain below 10 to the 10th coulombs, again differing by 20 orders of magnitude. Therefore, all astrophysical black holes are essentially Schwarzschild if non-rotating, or Kerr if rotating, with charge Q effectively exactly zero for all practical purposes. The Reissner-Nordström and Kerr-Newman solutions remain of primarily theoretical interest for studying black hole thermodynamics, testing quantum gravity theories, and exploring mathematical properties of general relativity. But they do not describe realistic astrophysical black holes found in nature. Gravitational waves ripples in spacetime. Einstein predicted in 1916 that accelerating masses emit gravitational waves, ripples in spacetime curvature that propagate outward at the speed of light, carrying energy and angular momentum away from their sources, analogous to how accelerating electric charges emit electromagnetic waves, but involving space-time geometry itself rather than electromagnetic fields. General relativity's highly nonlinear field equations admit wave solutions representing oscillating perturbations in space-time curvature travelling outward from sources, with the waves transverse oscillating perpendicular to propagation direction, and quadrupolar having spin 2 character, unlike electromagnetic radiation's dipole spin 1 character. Gravitational waves physically stretch space in one direction while compressing the perpendicular direction as they pass through a region, alternating the stretch and compression with each wave cycle, with amplitude decreasing inversely with distance from the source. For binary systems, 2 compact objects orbiting their common centre of mass, the quadrupole formula derived from linearized general relativity gives gravitational wave power radiated as p approximately equals 32 over 5 times. G to the 4th divided by c to the 5th times reduced mass squared times separation to the negative 4th power times angular velocity to the 6th power, where reduced mass equals m1 times m2 divided by m1 plus m2, separation is orbital separation, and angular velocity equals 2 pi divided by orbital period. This formula reveals several crucial points. Gravitational wave power scales as the 6th power of orbital velocity, making rapidly orbiting systems powerful emitters. Power increases as separation decreases to the negative 4th power, causing exponentially growing emission as binaries in spiral, and power scales with reduced mass squared, making massive compact binaries like black holes the strongest sources. This scaling shows the strongest gravitational wave emission comes from massive, compact objects in extremely close orbits, moving at relativistic speeds, exactly describing binary black hole or binary neutron star systems in the final moments before merger, when separations shrink to just a few Schwarzschild radii and orbital velocities reach 30 to 60% of light speed. At these extremes, gravitational wave luminosity can briefly exceed 10 to the 23rd solar luminosities, exceeding the electromagnetic luminosity of all stars in the observable universe combined by factors of thousands. Though radiating in spacetime ripples rather than photons, despite Einstein's 1916 prediction, decades passed before technology advanced sufficiently to detect these extraordinarily tiny spacetime ripples. Gravitational wave strain, fractional change in separation of test masses, for even the strongest sources at Earth is typically 10 to the minus 21st, requiring measuring changes in multi-kilometer baselines smaller than 1,000th the diameter of a proton. Joseph Weber pioneered gravitational wave detection in the 1960 seconds using resonant bar detectors, large aluminum cylinders, suspended and monitored for vibrations induced by passing gravitational waves, claiming detections in 1969 that were later discredited when other groups' similar detectors found nothing. Indirect evidence came first. Russell Hulse and Joseph Taylor's 1974 discovery of binary pulsar PSR-B 1913 plus 16, containing a pulsar with 59 millisecond period orbiting a companion neutron star with 7.75-hour orbital period, provided spectacular confirmation of gravitational radiation. By timing pulsar signals with microsecond precision over years, they measured orbital decay matching gravitational wave emission predictions to within 0.2%, proving gravitational waves exist and carry away energy exactly as Einstein's equations predict, earning the 1993 Nobel Prize in Physics. LIGO's first direct detection came the 14th of September 2015 at 9 hours 50 minutes and 45 seconds UTC, when both the Livingston, Louisiana, and Hanford, Washington interferometers, separated by 3,000 kilometers, simultaneously recorded a distinctive chirp signal lasting 0.2 seconds from a binary black hole merger designated GW150914, inaugurating the era of gravitational wave astronomy and confirming Einstein's century-old prediction that gravitational waves exist and can be detected. The signal showed the characteristic frequency increase, the chirp rising from 35 Hz to 250 Hz over 0.2 seconds, as two black holes with masses 36 and 29 solar masses spiraled together from separation of 350 kilometers down to merger, coalesced violently in a fraction of a second when their event horizons touched and merged, then rang down over several milliseconds as the perturbed final black hole with mass 62 solar masses settled to a stable Kerr solution by radiating away asymmetries through gravitational waves at quasi-normal mode. Frequencies. The detected strain, the fractional change in LIGO's 4-kilometer arm lengths, peaked at approximately 10 to the minus 21st, meaning the arms stretched and compressed by about 10 to the minus 18th meters, 1,000th the diameter of a proton, or about 1/1,000,000th the size of an atomic nucleus. Observing this infinitesimal signal required technological capabilities at the absolute limits of precision measurement. Exquisite vibration isolation using multiple-stage pendulum suspensions and active seismic isolation platforms to eliminate ground motion and vibrations from traffic, wind, ocean waves, and seismic events down to below 10 Hz, laser stabilization to parts per billion frequency stability using power and frequency stabilization servos, ultra-high vacuum systems, maintaining pressures below 10 to the -9th torr throughout 4-kilometer beam tubes to eliminate air molecules that would scatter laser light, and data analysis sophistication using matched filtering comparing observed data to libraries containing hundreds of thousands of theoretical waveform templates from numerical relativity simulations. The detection spectacularly confirmed Einstein's century-old prediction that accelerating masses produce gravitational radiation propagating at light speed, demonstrated that binary stellar mass black holes exist in nature and merge within cosmological timescales, and inaugurated gravitational wave astronomy as an entirely new observational window on the universe, complementing electromagnetic, neutrino, and cosmic ray astronomy. The signal's shape encoded rich information. Black hole masses, 36 and 29, solar masses, determined from chirp mass, measured during inspiral plus mass ratio, constrained from amplitude and frequency evolution. Final mass, 62 solar masses, measured from ring-down frequency, with 3 solar masses radiated as gravitational wave energy. More energy than all stars in the observable universe emit electromagnetically in the same time interval. Distance approximately 1.3 billion light-years, or redshift 0.09, determined from signal amplitude after accounting for masses and inclination. Final black hole spin, approximately 0.67, determined from ring-down frequency and damping time, and sky localization to approximately 600 square degrees, about 3,000 times the Moon's angular area, determined from millisecond time delays between detectors and amplitude, phase differences. The discovery earned the 2017 Nobel Prize in Physics for Rainer Weiss, Barry Barish, and Kip Thorne for decisive contributions to the LIGO detector and observation of gravitational waves. Binary black hole mergers proceed through 3 distinct phases observable in gravitational wave signals. The inspiral phase, lasting millions to billions of years as gravitational wave emission gradually shrinks the orbit. The merger phase, lasting a fraction of a second when horizons touch and violently coalesce, and the ring-down phase, lasting milliseconds as the perturbed final black hole settles to a stable Kerr solution by radiating asymmetries. During the long inspiral phase, orbital decay proceeds gradually. Gravitational wave emission carries away orbital energy at rate -dE/dt equals 32/5 times g to the 4th over c to the 5th times m1 cubed times m2 cubed times quantity m1 plus m2 to the -1 times separation to the -5th, and carries away angular momentum, causing separation to decrease, orbital velocity to increase, and orbital period to decrease. As separation shrinks, following approximately a to the -4 proportional to time, the orbital frequency rises as f proportional to a to the -3/2. Gravitational wave frequency, twice orbital frequency for quadrupole radiation, increases, and gravitational wave amplitude grows proportional to a to the -1. The inspiral phase is exceptionally well described by post-Newtonian approximations, systematic expansions of Einstein's equations in powers of velocity over c, valid when velocities are small compared to light speed, and spacetime curvature is weak. These approximations break down when orbital velocity reaches approximately 0, 3c to 0, 5c, and separation approaches a few Schwarzschild radii. LIGO's sensitive frequency band, extending from 10 Hz at low frequencies limited by seismic noise, to approximately 1000 Hz at high frequencies, limited by shot noise from laser photon statistics, captures the final seconds to minutes of inspiral when orbital velocities reach 30 to 60% light speed, plus the merger and ring down. For stellar mass black hole binaries with component masses 10 to 100 solar masses, the final inspiral stages lasting seconds sweep through LIGO's band, making LIGO exquisitely sensitive to these systems while being insensitive to more massive supermassive black hole binaries whose characteristic frequencies lie below 1 Hz. The merger phase, when event horizons physically touch, requires full numerical relativity simulations, solving Einstein's nonlinear field equations on supercomputers, as no analytic approximations remain valid in this regime where spacetime curvature and velocities approach maximum possible values. Numerical relativity breakthroughs in 2005 first achieved stable long-term simulations of binary black hole mergers after decades of attempts, revealing merger dynamics and waveforms. Ring down shows exponentially damped sinusoidal oscillations at quasi-normal mode frequencies, determined solely by final black hole mass, and spin the perturbed horizon vibrates like a struck bell ringing at characteristic tones with frequencies approximately 0.5 to 1 times cubed over GM and damping times 10 to 100 times GM over cubed, depending on spin and overtone numbers. LIGO and Virgo have detected approximately 90 gravitational wave events confidently in the first 3 observing runs, 01, 02, and 03, spanning 2015 to 2020, predominantly binary black hole mergers with component masses ranging from 5 to 150 solar masses, with several binary neutron star mergers and 1 potential neutron star black hole merger, revolutionizing our understanding of compact object populations, binary evolution, merger rates, and strong field gravity. The landmark event GW170817, detected August 17, 2017, involved binary neutron stars, with masses approximately 1.46 and 1.27 solar masses, merging at distance 40 megaparsecs, 130 million light-years, and was accompanied by electromagnetic counterparts, including a short gamma-ray burst detected 7 seconds after merger by Fermi and integral satellites, an optical infrared kilonova resulting from R-process nucleosynthesis in neutron-rich ejecta, synthesizing half the periodic table's heavy elements, including gold and platinum, and late-time radio emission from jet cocoon interaction, enabling unprecedented multi-messenger astronomy, combining gravitational waves with electromagnetic observations across the spectrum. The GW170817 observations confirmed that binary neutron star mergers produce short gamma-ray bursts, resolving a decades-old debate, demonstrated that heavy element synthesis through rapid neutron capture occurs in neutron star mergers, producing gold, platinum, and other elements essential for technology, constrained neutron star equation of state through tidal deformability measurements, showing neutron stars are less deformable than some soft equations of state predicted, and enabled novel cosmological measurements, including Hubble constant determination at 70 km per second per megaparsec, independently of cosmic distance ladder. The detected population of black hole mergers reveals intriguing properties. Mass distribution shows peaks around 10 and 35 solar masses, with possible gap from 50 to 130 solar masses, where pair instability supernovae should prevent black hole formation from stellar evolution, though several events, including GW 190521, contain black holes in this gap, suggesting hierarchical mergers or alternative formation channels. Spin distribution shows most black holes have small, dimensionless spins, less than 0.5, with some systems showing higher spins and spin misalignments relative to orbital angular momentum, indicating possibly dynamical formation in dense clusters rather than isolated binary evolution. Merger rates of approximately 50 per cubic gigaparsec per year for binary black holes and approximately 300 per cubic gigaparsec per year for binary neutron stars constrain stellar evolution models and binary formation scenarios. Some detected systems, like GW 190521, with component masses 85 and 66 solar masses, producing 142 solar mass final black hole, firmly in intermediate mass range challenge formation models and reveal. Black holes form in unexpected mass ranges through mechanisms not yet understood. Gravitational wave detections test general relativity in the strong field regime near black holes, where previous tests were impossible. With all observations to date showing perfect agreement with Einstein's predictions, no deviations detected in dispersion, gravitational waves travel at light speed. Polarization, consistent with spin 2 prediction, in spiral evolution matches post-Newtonian predictions, or ring-down frequencies match Kerr quasi-normal modes, and constraining Hubble constant independently to approximately 70 plus or minus 10 km per second per megaparsec through standard siren technique using gravitational wave distance measures combined with electromagnetic redshift measurements. Primordial black holes relics from the Big Bang. Primordial black holes hypothetically formed in the early universe's first second through direct collapse of overdense regions in the primordial plasma, offering a formation mechanism completely and fundamentally distinct from stellar core collapse that produces stellar mass black holes billions of years later, or gradual accumulation in galactic centers that builds supermassive black holes over cosmological timescales. Unlike stellar mass and supermassive black holes, which form from matter that has evolved for millions or billions of years through nuclear fusion, chemical enrichment, and hierarchical structure formation, primordial black holes could have formed directly from the initial density fluctuations immediately after the Big Bang, when the universe was extremely hot, dense, and radiation dominated, with temperatures exceeding billions of degrees and densities exceeding nuclear density. If quantum fluctuations during the inflationary epoch that occurred approximately 10 to the minus 35th seconds after the Big Bang, or phase transitions in the early universe, such as the quark-hadron transition, or the collapse of cosmic strings or domain walls, produced regions with density exceeding a critical threshold approximately 50% above the background density. Those overdense regions would collapse gravitationally once their size came within their own gravitational radius, essentially their Schwarzschild radius. When the Hubble radius during the radiation-dominated era equaled the collapsing region's size, that region would fall out of causal contact with its surroundings and collapse into a black hole with mass approximately equal to the Hubble mass at that cosmic time, given by m approximately equals cubed times t divided by 2g, where t is the cosmic time when collapse occurred. Primordial black holes could have masses spanning an utterly enormous range, from microscopic masses at the Planck mass of approximately 10 to the minus 8th kilograms, 22 micrograms, the lightest possible black holes. Before quantum gravity effects dominate up to thousands or potentially millions of solar masses, covering 46 orders of magnitude in mass and including ranges completely impossible for stellar origin black holes, which are restricted to approximately 3 solar masses, at minimum the Tolman-Oppenheimer-Volkoff, up to perhaps 300 solar masses at maximum from stellar evolution. The formation time determines the primordial black hole mass. Black holes forming at Planck time 10 to the minus 43rd seconds would have Planck mass 10 to the minus 8th kilograms. Forming at 10 to the minus 24th seconds during quark-hadron transition would have masses around 1 kilogram to 10 kilograms. Forming at 1 second when universe had temperature 10 billion, Kelvin would have masses approximately 10 to the 5th solar masses. Forming during later times would produce even more massive primordial black holes. This mass formation time relationship follows from m approximately proportional to t during radiation domination, meaning primordial black hole mass directly records the cosmic epoch when it formed. Different formation mechanisms might produce primordial black holes in specific narrow mass ranges or extended broad mass ranges depending on the spectrum of initial density fluctuations and the physical processes operating at different epochs. Primordial black holes with masses below approximately 10 to the 15th grams, about the mass of a large mountain or small moon, would have completely evaporated by the present day through Hawking radiation, as black holes with these masses have Hawking temperatures exceeding 100 Kelvin and evaporation timescales shorter than the universe's 13.8 billion year age. The evaporation timescale scales as m cubed. Specifically, T approximately equals 5,120 pi times g squared times m cubed divided by h bar c to the fourth, where h bar is reduced Planck constant, working out to approximately 2.1 times 10 to the minus 67th times quantity m over kilograms cubed years. For a black hole with mass 10 to the 11th kilograms, evaporation time approximately equals the current age of the universe, 13.8 billion years, meaning black holes lighter than this critical mass have evaporated. These evaporating primordial black holes would produce distinctive signatures, including bursts of high-energy particles and gamma rays, as the final explosion occurs when the black hole shrinks to Planck scale, and a diffuse background of particles and radiation from evaporation throughout cosmic history. Searches for these signatures, including monitoring for gamma-ray bursts from nearby evaporating primordial black holes and measuring diffuse gamma-ray background, have found no convincing evidence constraining primordial black hole abundance in this low mass range. Heavier primordial black holes, above 10 to the 15th grams, survive to the present and could potentially constitute a fraction of the universe's dark matter if they formed in sufficient numbers and with appropriate mass distribution. They could constitute a non-negligible or even dominant fraction of the universe's dark matter if primordial black holes formed in significant numbers with appropriate mass distribution concentrated in ranges where observational constraints are weakest, particularly intermediate masses around 10 to the 20th to 10 to the 26th grams, asteroid to moon mass, where microlensing constraints have gaps. Though most formation models and observational constraints suggest primordial black holes probably comprise less than 1 to 10% of dark matter. The dark matter hypothesis for primordial black holes is attractive because black holes are naturally dark, emitting no electromagnetic radiation except negligible Hawking radiation, and interact only gravitationally, matching dark matter's observed properties. Primordial black holes could explain dark matter without invoking exotic beyond standard model particles, like WIMPs, axions, or sterile neutrinos. However, primordial black holes face significant observational constraints from multiple channels that have progressively tightened over decades of searches. Gravitational microlensing surveys, including MACO, EROS, and OGLE, monitoring millions of stars in the Large and Small Magellanic Clouds and Galactic Bulge, have searched for brightening events when primordial black holes pass between Earth and background stars, finding far fewer events than expected if primordial black holes dominated dark matter, constraining primordial black hole abundance to less than 10% of dark matter for masses 10 to the negative 7th to 10, solar masses with strongest constraints around 0.5 solar masses, where lensing is most easily detected. Searches for primordial black holes use multiple complementary techniques spanning electromagnetic, gravitational wave, and structure formation observations. Gravitational microlensing surveys monitoring millions of stars detect temporary brightening when primordial black holes pass between Earth and background stars, constraining abundance for masses 10 to the negative 10th to 100 solar masses. Femtolensing of gamma-ray bursts, where primordial black holes in the beam path would create achromatic brightness variations on microsecond timescales, constraints masses 10 to the 17th to 10 to the 20th kilograms. Cosmic microwave background observations constrain primordial black hole formation because accretion during recombination would inject energy affecting CMB temperature and polarization, limiting abundance below 10 to the negative third of dark matter for masses below 10 to the fourth solar masses. Structure formation constraints from the first stars and galaxies require dark matter to cluster hierarchically, disfavoring scenarios where significant fraction of dark matter is in massive primordial black holes exceeding 10 solar masses. Dynamical constraints from wide binary star disruption in the galactic disk constrain primordial black holes with masses 5 to 300 solar masses to below 10% of dark matter. Pulsar timing array observations, searching for gravitational wave signatures from primordial black hole binaries, in spiraling constrain certain mass and abundance combinations, and ultra-faint dwarf galaxy survival places limits on primordial black holes through gravitational heating that would disperse these fragile systems. Effects on structure formation provide powerful constraints because primordial black holes present at recombination and matter radiation equality would affect how cosmic structures grow, with their gravitational influence different from smoothly distributed particle dark matter. If primordial black holes exceeding 10 to the 30th grams, approximately 1 solar mass, comprised significant fractions of dark matter, their discreteness and shot noise would enhance small-scale density fluctuations, potentially overproducing early structure formation and creating more dwarf galaxies than observed. Conversely, lighter primordial black holes below 10 to the 26th grams moving at high velocities in early universe would erase small-scale structure through dynamical friction and Poisson noise, conflicting with observations of Lyman alpha forest showing small-scale structure at high redshifts. Intermediate masses around 10 to the 20th to 10 to the 24th grams fall in a window where multiple constraints weaken, and some studies suggest primordial black holes in this range could constitute 10 to 100% of dark matter without definitively violating current observational limits. The Nanograv 2023 detection of a possible gravitational wave background signal at nanohertz frequencies might potentially arise from inspiraling primordial black hole binaries in this mass range, though supermassive black hole mergers remain the more conventional explanation. Recent microlensing observations by HSC Survey and Subaru Telescope monitoring Andromeda Galaxy found possible excess of short timescale microlensing events consistent with primordial black holes around 10 to the negative fifth. Solar masses comprising perhaps 0.1% of dark matter, though interpretation remains debated. Current consensus based on combined constraints suggests primordial black holes probably comprise less than 1 to 10% of total dark matter across most mass ranges, with windows remaining open around 10 to the negative 12th solar masses, asteroid mass, 10 to the negative 5th to 10 to the negative 2nd solar masses, terrestrial planet mass, and potentially 10 to the 2nd solar masses, intermediate mass, where constraints weaken and primordial black holes could contribute non-negligibly. Future gravitational wave observations by LIGO, Virgo, CAGRA continuing. Space-based LISA mission detecting millihertz gravitational waves from intermediate mass black hole binaries. Improved microlensing surveys with higher cadence and larger numbers of monitored stars. James Webb Space Telescope observations of first galaxies constraining early structure formation, and CMB observations with improved sensitivity and angular resolution will further test primordial black hole scenarios and potentially discover evidence for this exotic dark matter candidate, or rule it out across remaining mass windows. The search for primordial black holes represents a fascinating intersection of cosmology, gravitational physics, dark matter, astrophysics, and observational astronomy, with potential to revolutionize our understanding of the early universe, dark matter's nature, and black hole populations if detected, or to further constrain formation mechanisms and initial conditions if definitively ruled out. Black hole mergers, cosmic collisions. Binary black hole systems lose energy through gravitational wave emission, causing orbital decay that eventually leads to merger. Two black holes in orbit around their common center of mass continuously radiate gravitational waves, carrying away energy and angular momentum. This gravitational radiation back reaction causes the orbital separation to decrease and orbital frequency to increase in a process called in-spiral. For stellar mass black holes separated by typical distances, in-spiral proceeds extremely slowly. Initially, 230 solar mass black holes separated by 100 astronomical units would take trillions of years to merge through gravitational radiation alone. But as separation decreases, gravitational wave emission increases dramatically, scaling as the sixth power of orbital frequency. Once separation shrinks to a few Schwarzschild radii, the in-spiral accelerates rapidly, with the final plunge from separation of 10 Schwarzschild radii to merger occurring in just fractions of a second. During this final phase, orbital velocities reach 30 to 60% of light speed. Gravitational wave frequencies sweep through LIGO's sensitive band of 10 to 1000 Hz, and emitted gravitational wave power can briefly exceed the electromagnetic luminosity of all stars in the observable universe combined. The final plunge and merger phase lasts just a fraction of a second as the two event horizons approach, touch, and violently merge into a single highly distorted horizon. This merger phase cannot be described by post-Newtonian approximations that work well during in-spiral. It requires solving Einstein's full non-linear field equations using numerical relativity simulations on supercomputers. As horizons touch, space-time geometry undergoes dramatic changes. The individual horizons merge and expand, forming a common event horizon that initially has complex, non-spherical shape with peaks, valleys, and dynamic distortions. During merger, approximately 3 to 5% of the total system mass converts to gravitational wave energy radiated in less than 1 second. For 230 solar mass black holes merging, this means roughly 2 solar masses equivalent to 4 times 10 to the 47th joules radiates as gravitational waves. The peak gravitational wave luminosity during merger can reach 10 to the 23rd solar luminosities, making these briefly the most luminous events in the universe, though emitting energy as space-time ripples rather than electromagnetic radiation. Ring-down follows merger as the perturbed final black hole settles to a stable Kerr solution through exponentially damped oscillations at characteristic quasi-normal mode frequencies. The merged black hole emerges highly distorted and dynamically vibrating. These vibrations dissipate through gravitational wave emission over timescales of milliseconds, with the horizon oscillating at specific frequencies determined solely by the final black hole's mass and spin the quasi-normal modes. Like a struck bell ringing at characteristic frequencies determined by its size and composition, the newly merged black hole rings at frequencies encoded in its mass and spin. For a 60 solar mass black hole, the fundamental quasi-normal mode frequency is approximately 250 Hz, with damping time roughly 5 milliseconds. The ring-down signal contains less energy than the merger, but carries clean information about the final black hole's properties. Observing ring-down allows testing the no-hair theorem, verifying that the final object is indeed a Kerr black hole characterized only by mass and spin, with no additional structure or deviations from general relativity's predictions. Asymmetric gravitational wave emission during merger can impart recoil velocities or kick velocities to the final black hole, potentially reaching thousands of kilometers per second and occasionally ejecting merged black holes from their host galaxies. When two black holes merge with unequal masses, unequal spins, or spins misaligned with orbital plane, the gravitational waves emitted preferentially in certain directions carry net linear momentum. Conservation of momentum requires the merged black hole to recoil in the opposite direction. Kick velocities depend on mass ratio, spin magnitudes, and spin orientations, with maximum kicks around 5,000 kilometers per second for specific configurations involving nearly equal mass black holes with large spins anti-aligned with orbital angular momentum. These velocities can exceed escape velocities from globular clusters around 50 kilometers per second and dwarf galaxies around 100 kilometers per second, and approach escape velocities from massive galaxies around 500, 1,000 kilometers per second. Recoiling black holes appear as off-center active galactic nuclei displaced from host galaxy cores, with several candidates identified, including quasar CID42 offset by 2 kiloparsecs from its galaxy center. Hierarchical mergers build up massive black holes through successive generations, where merger products merge again, potentially explaining formation of black holes in pair instability mass gap and growth of intermediate mass black holes. In dense stellar environments like globular clusters and nuclear star clusters, stellar mass black holes can merge, producing black holes with masses 50 to 150 solar masses. These intermediate mass merger products can subsequently merge with other black holes, building up even more massive objects through hierarchical assembly. This scenario became observationally relevant when LIGO detected events like GW 190521 involving black holes with masses in the pair instability gap where stellar evolution cannot produce black holes directly. The progenitor black holes must have formed through previous mergers rather than stellar collapse. Hierarchical mergers also provide pathway for growing intermediate mass black holes to masses exceeding 1,000 solar masses. Computer simulations of dense star clusters show hierarchical mergers can produce black holes up to approximately 0.1% of cluster mass, potentially creating intermediate mass black holes of 10,000 solar masses in massive globular clusters. Population synthesis models predict merger rates by simulating evolution of millions of binary systems, from formation through potential merger, accounting for stellar evolution, binary interactions, supernova kicks, and gravitational wave emission. These models track binaries through complex evolutionary pathways, including common envelope phases, where one star engulfs its companion, mass transfer episodes where one star feeds the other, and tidal interactions. Different formation channels produce different merger rate predictions and black hole mass distributions. Isolated binary evolution in galactic fields produces merger rates around 10 to 100 per cubic gigaparsec per year, with typical masses 5 to 30 solar masses. Dynamical formation in dense clusters through three-body encounters, assembling binaries and hardening through additional encounters, produces higher masses and potentially higher rates. Primordial binaries forming in the early universe could merge at high redshifts. LIGO-Virgo observations constrain these models, favoring scenarios producing merger rates approximately 50 per cubic gigaparsec per year and allowing formation of black holes up to 100 solar masses. Gravitational wave observations reveal merger rates increase with redshift, indicating merger rate density was higher in the past when the universe was younger and star formation rates were higher. LIGO-Virgo detections extend to redshifts around 1, corresponding to lookback, times 6 to 8 billion years. The merger rate per comoving volume appears to increase by factors of 5 to 10 from today to redshift 1, tracking star formation rate evolution. This implies most mergers occurred billions of years ago during peak star formation era. Future gravitational wave detectors like Einstein telescope will observe mergers to redshift 10 and beyond, potentially detecting mergers involving first-generation black holes from population 3 stars. Studying merger rate evolution constrains star formation history, binary evolution physics, and time delays between binary formation and eventual merger. Mergers also produce heavy elements including gold and platinum through R-process nucleosynthesis in neutron star mergers, enriching the universe with elements essential for rocky planets and life. Jets and outflows cosmic particle accelerators. Relativistic jets launched from active galactic nuclei and microquasars represent the universe's most powerful particle accelerators, accelerating plasma to velocities exceeding 99% of light speed and extending across millions of light years, creating some of the most spectacular structures observed in the cosmos. These jets originate from regions within just a few gravitational radii of black hole event horizons, typically 1 to 10 times the Schwarzschild radius, or roughly 30 to 300 kilometers, for stellar mass black holes, and 10 million to 100 million kilometers for supermassive black holes, where magnetic fields threading through the ergosphere and event horizon extract rotational energy from spinning black holes through magnetohydrodynamic processes and convert it into kinetic energy of outflowing plasma and electromagnetic Poynting flux. The jets are launched perpendicular to the accretion disk plane along the black hole's rotation axis, forming bipolar structures with oppositely directed flows on either side. Jets are observed across the entire electromagnetic spectrum, from radio through optical to X-rays and gamma rays, with different emission mechanisms dominating at different wavelengths, revealing complementary aspects of jet physics. Radio observations at frequencies 100 MHz to 100 GHz reveal large-scale jet structure extending from kiloparsecs to megaparsecs, traced by synchrotron emission from relativistic electrons spiraling in magnetic parsecs. Optical observations show discrete knots of emission along jets marking shocks where particle acceleration occurs. X-ray observations trace high-energy particle populations through synchrotron or inverse Compton emission, revealing the most energetic particles. Gamma-ray observations detect emission from relativistic shocks and particle acceleration sites where protons and electrons reach energies exceeding 10 to the 12th electron volts. The jets carry enormous power ranging from 10 to the 42nd ergs per second for microquasars containing stellar mass black holes, up to 10 to the 47th ergs per second for the most powerful AGN jets from supermassive black holes, power output sufficient to affect the evolution of entire galaxies and galaxy clusters through mechanical and radiative feedback, heating surrounding gas over hundreds of millions to billions of years. For comparison, 10 to the 47th ergs per second equals approximately 100 billion times the Sun's luminosity, or 1,000 times the total luminosity of the Milky Way galaxy, concentrated in narrow jets, just kiloparsecs across. The total energy delivered by jets over their active lifetimes of 10 million to 100 million years reaches 10 to the 60th to 10 to the 61st ergs, comparable to the gravitational binding energy of entire galaxy. Bulges containing 100 billion stars. This enormous energy injection fundamentally affects galaxy evolution by heating the circumgalactic and intracluster medium, driving turbulence, inflating giant bubbles displacing hot gas, and regulating when and where stars form by controlling gas thermodynamic state. Without AGN jet feedback, massive galaxies and galaxy clusters would evolve completely differently, converting far more gas into stars than observed, and failing to maintain the hot X-ray emitting atmospheres that surround them. The Blandford-Znajek mechanism extracts black hole rotational energy electromagnetically by threading magnetic fields through the ergosphere and event horizon, and converting frame dragging of space-time into electromagnetic, pointing flux flowing outward along the rotation axis, providing the engine that powers relativistic jets. Magnetic field lines are anchored in the surrounding accretion disk, where differential rotation and turbulent dynamos generate strong toroidal and poloidal magnetic fields, reaching strengths 100 to 10,000 Gauss. Some field lines extend inward through the ergosphere, the region outside the event horizon, where frame-dragging forces all observers to co-rotate and thread through the event horizon itself. Frame dragging caused by the black hole's rotation physically drags space-time around, and the magnetic field lines frozen into the rotating space-time are twisted around the rotation axis, much like twisting a towel wrings water from it. This twisting of magnetic field lines induces electric fields parallel to the magnetic field through Faraday's law of electromagnetic induction. The changing magnetic flux through loops creates electromotive force, driving charges to flow. The induced electric fields accelerate charged particles, electrons, and ions, creating electric currents that flow along the twisted magnetic field lines from the disk through the ergosphere and outward along the rotation axis. These currents transport electromagnetic energy in the form of pointing flux energy carried by electromagnetic fields propagating as waves that flows outward along the rotation axis, forming the collimated electromagnetic jet structure. The power extracted through Blandford-Znajek mechanism scales as omega h squared times b squared times rh to the fourth power, where omega h is the angular velocity at the black hole horizon proportional to the spin parameter. B is the magnetic field strength threading the horizon, and RH is the horizon radius proportional to black hole mass. The horizon angular velocity, omega h, equals a times c, divided by 2 gm, where a is the dimensionless spin parameter ranging from 0 to 1, showing that rapidly spinning black holes with a approaching 1 have much higher angular velocities and therefore much greater power extraction. For rapidly spinning black holes with spin parameters are greater than 0.9 and near horizon magnetic field strengths 1000 to 10,000 Gauss strengths consistent with observations and magnetohydrodynamic simulations of accretion disk, magnetic field amplification through magnetorotational instability. Blandford's Znarjek power can reach 10 to the 45th ergs per second for supermassive black holes with masses 1 billion solar masses, sufficient to power the most luminous, observed relativistic jets, extending megaparsecs and inflating giant radio lobes. The mechanism efficiently converts up to 29% of a maximally spinning black hole's rotational energy into jet power, though typical efficiencies are 1 to 10% depending on magnetic field geometry and strength. Jet collimation by magnetic fields near the base and external pressure confinement at larger distances maintain narrow opening angles less than 5 degrees across scales, spanning 6 to 7 orders of magnitude from sub-parsec to megaparsec distances from gravitational radii near the black hole to scales comparable to galaxy sizes and beyond. Near the jet base, within approximately 100 gravitational radii, or roughly 0.01 parsecs for supermassive black holes, toroidal magnetic fields, generated by electric currents, flowing along poloidal field lines, create magnetic hoop stress, inward magnetic pressure from the tension in toroidal field components, wrapped around the jet like hoops around a grate. Barrel that confines the jet against its own internal pressure gradients. This magnetic self-collimation through hoop stress keeps the jet narrow and focused, preventing it from expanding radially and dissipating its energy. The collimation is most effective when the magnetic field has strong toroidal component comparable to or exceeding the poloidal component, creating substantial hoop stress. At larger distances beyond approximately 1000 gravitational radii, or 0.1 to 1 parsec where magnetic hoop stress weakens, interaction with the external medium surrounding the jet provides additional collimation. The lower density relativistic jet plasma is surrounded by higher density ambient gas, either the interstellar medium within the host galaxy or the hot intracluster medium in galaxy clusters, creating pressure gradients that force the jet to remain narrow through external confinement. If the jet attempts to expand, the surrounding higher pressure medium compresses it back. Very long baseline interferometry observations, achieving sub-milliarc second angular resolution by combining radio telescopes across continents, have resolved jet collimation establishing on parsecant scale distances from supermassive black holes in nearby AGN, including M87, Cygnus A, and 3C273, directly confirming that jets emerge already well collimated within 10 to 100 Schwarzschild radii from the black hole and maintain collimation across parsec to kiloparsec scales. Jets maintain this remarkable collimation across 6 to 7 orders of magnitude in linear distance from sub-parsec scales near the black hole where jets are light months across, to megaparsec scales where jets span millions of light years, yet remain collimated within opening angles 3 to 5 degrees, indicating that both magnetic self-collimation operating near the base and external pressure confinement at larger distances must contribute cooperatively. Jet stability additionally requires careful balance between multiple pressure components, including magnetic pressure from field tension, thermal gas pressure from heated plasma, and ram pressure from bulk flow momentum. with any imbalance causing jet disruption through kink instabilities, pinch instabilities, or Kelvin-Helmholtz instabilities along jet boundaries. AGN feedback from jets and radiation regulates star formation in massive galaxies by heating or expelling gas that would otherwise cool and form stars, preventing runaway cooling in galaxy clusters, and explaining why most massive galaxies are red and dead with little ongoing star formation despite containing abundant gas. Simulations of galaxy formation and evolution that do not include AGN feedback produce catastrophic failures when compared to observations, generating far too many massive galaxies with too many stars, excessive star formation rates in massive systems, and galaxy colors that are too blue, indicating ongoing star formation, when observations show massive galaxies are predominantly red and quiescent. Including AGN feedback in simulations, specifically energy and momentum injection from jets driving shocks and turbulence, plus radiation pressure from accretion disk emission during high luminosity phases, dramatically reduces star formation in massive galaxies by heating gas to temperatures exceeding 10 million Kelvin, where cooling times become longer than dynamical times, or by expelling gas entirely from galaxies through powerful winds, successfully reproducing the observed galaxy luminosity function with correct abundances at all masses. The color magnitude bimodality showing red and blue populations, and the morphology density relation where massive elliptical galaxies dominate dense environments. Two distinct AGN feedback modes operate in different accretion regimes. Quasar mode involving powerful radiation pressure and winds during high accretion phases when black holes accrete near the Eddington limit, expelling gas from galaxies through radiatively driven outflows, and radio mode involving mechanical heating by jets during low accretion phases, maintaining gas in hot ionized state, preventing cooling and star formation. In massive galaxy clusters containing thousands of galaxies and copious hot X-ray emitting intracluster medium, radio mode feedback is especially important and operates continuously over billions of years. Jets launched from the central supermassive black hole in the brightest cluster galaxy inflate giant cavities or bubbles in the X-ray gas extending 10 to 100 kiloparsecs, displacing hot gas and driving shocks and turbulence that heat the gas through shock dissipation and turbulent cascade. The mechanical power delivered by jets measured from cavity enthalpy divided by age reaches 10 to the 44th to 10 to the 45th ergs per second, remarkably matching the radiative cooling luminosity from X-ray emission, demonstrating that jet heating precisely balances cooling and prevents the cooling catastrophe. Microquasars are stellar mass black hole versions of AGN, showing remarkably similar phenomenology, including relativistic jets, variable accretion, states transitioning between disk-dominated and corona-dominated emission, and X-ray emission with characteristic power law spectra and temporal variability, providing accessible laboratories for studying jet physics and accretion ejection coupling in compact systems with timescales compressed by factors of millions compared to supermassive black holes. SS 433, discovered in 1979, displays relativistic jets with velocity 0.2, 6 times light speed corresponding to Lorentz factor 1.04, precessing with 162-day period due to precession of the accretion disk, creating distinctive corkscrew or helical jet pattern observable in radio maps and optical spectroscopy, showing moving emission line components. GRS 1915 plus 105 contains a black hole with mass 10 to 18 solar masses, showing extraordinarily complex behavior. including at least 12 distinct accretion states. Superluminal jet motions, with apparent velocities exceeding 1.5 times light speed due to relativistic projection effects when jets aimed nearly toward Earth. And quasi-periodic oscillations at frequencies 40 to 450 Hz, reflecting orbital dynamics and oscillations near the innermost stable circular orbit, just 3 to 6 Schwarzschild radii from the horizon. Cygnus X1 and Cygnus X3 also display jet activity, with radio flares correlated to X-ray spectral state changes, demonstrating coupling between accretion flow geometry and jet launching. Microquasars provide testbeds for understanding how accretion rate, accretion disk state, including transitions between thin disk and thick disk, or advection-dominated accretion flow geometries, and black hole spin determine jet power, velocity, and duty cycle, with timescales compressed from millions of years for AGN variability to days or weeks for microquasars, enabling study of complete cycles within human lifetimes. Galaxy evolution, the role of black holes. The M-sigma relation correlates supermassive black hole mass with host galaxy bulge, velocity dispersion, revealing the profound and surprising fact that black holes and galaxies co-evolve in lockstep, despite black holes being physically 1 million times smaller than their host galaxies and containing only 1 to 0.2% of the bulge stellar mass. The empirical correlation, discovered independently by several groups around the year 2000 through observations of nearby galaxies, takes the mathematical form MBH equals approximately 10 to the 8.1 solar masses times the quantity sigma divided by 200 kilometers per second raised to the 4.4 power, where MBH is the supermassive black hole mass and sigma is the stellar velocity dispersion, the root mean square velocity of stars in random directions within the galaxy bulge, measured from Doppler broadening of absorption, lines in galaxy spectra. This steep power law with exponent 4.4 shows black hole mass increases extremely rapidly with velocity dispersion. Doubling velocity dispersion from 200 to 400 kilometers per second increases black hole mass by factor 2 to the 4.4 equals approximately 21, showing that more massive galaxies have disproportionately more massive central black holes. The correlation spans enormous dynamic range, from dwarf galaxies with velocity dispersions 50 kilometers per second hosting black holes of 10 to the 5th solar masses, up through giant ellipticals with dispersions 300 kilometers per second hosting black holes exceeding 10 to the 9th solar masses over 4 orders of magnitude in both quantities. The relation's remarkable tightness with observed scatter only 0.3 to 0.5 Dex factors of 2 to 3 around the best fit correlation across diverse galaxy types, including ellipticals, classical bulges in spiral galaxies, and some pseudo-bulges implies genuine physical connection between black hole growth and galaxy evolution, rather than coincidental correlation or indirect relationship through third variable. If black hole growth and galaxy growth were independent processes occurring without mutual influence or common driver, the scatter would be much larger, reflecting random variations in both quantities. The tight correlation suggests that black hole mass and bulge properties are causally connected through physical mechanisms operating during galaxy formation and evolution. Since velocity dispersion measures the gravitational potential depth of the galaxy bulge, higher velocity dispersion means deeper potential, requiring more mass to produce the observed stellar velocities. The correlation ultimately relates black hole mass to the total mass in stars, gas, and dark matter within the bulge. The physical origin of the relation likely involves multiple mechanisms. AGN feedback, where growing black holes inject energy and momentum, affecting surrounding gas and regulating star formation rates. Common gas supply, where processes like galaxy mergers deliver gas simultaneously, fueling central black hole accretion and triggering starbursts in the bulge. And self-regulation, where black hole growth and star formation mutually influence each other through feedback loops, operating over millions to billions of years during hierarchical galaxy assembly. Black hole mass is approximately 0.1 to 0.2% of bulge stellar mass for typical galaxies, though this ratio shows more scatter than the M-sigma relation and varies systematically with galaxy type. Classical bulges formed through mergers show tighter correlation than pseudo-bulges formed through secular disk instabilities. For example, the Milky Way's bulge contains approximately 2 times 10 to the 10th solar masses in stars, while Sagittarius A times contains 3 million solar masses, giving ratio 0.02%, slightly below typical. Giant elliptical galaxy M87 has bulge mass approximately 10 to the 12th solar masses, with central black hole 6.5 billion solar masses, giving ratio 0.65% above average. This small mass fraction means black holes themselves contribute negligibly to galaxy gravitational potentials and dynamics. The black hole's sphere of influence, where its gravity dominates, extends only to approximately 10 to 100 parsecs, tiny compared to galaxy sizes of 10 to 100 kiloparsecs. Yet despite this tiny mass fraction, black holes profoundly influence galaxy evolution through their enormous energy output during active accretion phases, when they convert 10 to 42% of accreted rest mass into radiation and kinetic energy via jets and winds, vastly exceeding energy output from all stellar processes combined. This connection between black holes and galaxies likely arises through multiple interrelated physical mechanisms operating across cosmic time. AGN feedback, where growing black holes inject mechanical and radiative energy affecting star formation. Mergers and interactions that funnel gas toward galactic centers, simultaneously fueling black hole accretion and starbursts. And self-regulation through negative feedback loops, where AGN activity heats or expels gas, thereby limiting both its own fuel supply and the gas available for forming stars. During major galaxy mergers, when 2 comparable mass galaxies collide, gravitational torques drive large quantities of gas, tens of billions of solar masses, toward the merger remnant center on timescales of tens of millions of years. This gas forms stars at prodigious rates, reaching 100 to 1,000 solar masses per year in starburst phase, while simultaneously feeding the central supermassive black holes, which grow rapidly through gas accretion. The M-sigma relation allows astronomers to estimate black hole masses in distant galaxies, where direct dynamical mass measurements through stellar or gas kinematics are impossible due to insufficient angular resolution or brightness. By measuring velocity dispersion through spectroscopy and applying the calibrated relation, black hole masses at high redshift can be estimated, revealing that billion solar mass black holes existed when the universe was less than 1 billion years old. Quasar mode feedback during high accretion phases produces powerful radiation-driven winds and pressure that expel gas from galaxies at velocities reaching thousands to tens of thousands of kilometers per second, potentially quenching star formation and transforming galaxies from blue star-forming systems to red quiescent systems. When supermassive black holes accrete gas at rates approaching the Eddington limit during merger-driven gas inflows, they generate bolometric luminosities exceeding 10 to the 46th ergs per second, equivalent to 100 trillion suns. At these extreme luminosities, radiation pressure on dust grains and Thomson's scattering off electrons become dynamically important forces, accelerating gas outward and launching powerful winds at velocities 500 to 3,000 km per second for warm ionized gas, up to 0.1 to 0.3 times light speed for ultra-fast outflows detected through blue-shifted X-ray absorption lines. These outflows carry enormous kinetic power, with mass outflow rates reaching 100 to 1,000 solar masses per year, comparable to or exceeding star formation rates in host galaxies. The mechanical power in outflows reaches 10 to the 43rd to 10 to the 45th ergs per second, representing 0.5 to 5% of AGN bolometric luminosity coupled into winds. These powerful winds can clear gas from the central kiloparsec of galaxies over timescales of 1 to 10 million years, removing fuel for both star formation and continued black hole accretion, shutting down both processes simultaneously in negative feedback loop. Observations provide compelling evidence. Ultra-fast outflows with velocities 0.1 to 0, 3c, detected in approximately 40% of luminous AGN through highly blue-shifted X-ray absorption features. Warm, ionized outflows with velocities 500 to 2,000 km per second, extending across 1 to 10 kiloparsecs, detected through broad blue-shifted AFE emission lines. And molecular gas outflows with velocities 500 to 1,000 km per second, carrying 10 to the 8th to 10 to the 9th solar masses detected through CO emission kinematics. Quasar mode feedback is especially important during galaxy mergers, which trigger simultaneous starburst activity and black hole growth, with AGN feedback eventually expelling remaining gas and transforming blue star-forming galaxies into red quiescent galaxies. This transformation helps explain the bimodality in galaxy color magnitude diagrams showing distinct populations of blue star-forming and red quiescent galaxies, suggesting rapid quenching timescales consistent with AGN feedback. Radio mode mechanical feedback from relativistic jets during low accretion phases maintains gas in hot state in massive galaxies and galaxy clusters, preventing the cooling catastrophe where gas should rapidly cool and form stars at rates orders of magnitude higher than observed. In galaxy cluster cores, where gas densities reach 0.01 to 0.1 particles per cubic centimeter at temperatures 10 to the 7th to 10 to the 8th Kelvin, cooling times work out to 10 to the 8th to 10 to the 9th years shorter than cluster ages. Gas should cool and collapse, forming cooling flows with infall rates 100 to 1,000 solar masses per year. But observations show actual star formation rates 100 to 1,000 times lower, indicating heating prevents cooling. Radio observations reveal powerful jets from central AGN in brightest cluster galaxies, inflating giant cavities in X-ray gas with sizes 10 to 100 kiloparsecs. Cavity powers determined from pressure times volume divided by age reach 10 to the 44th to 10 to the 45th ergs per second, remarkably matching cooling luminosities from X-ray emission, demonstrating jet mechanical power precisely balances radiative cooling. Jets drive shocks with Mach numbers 1.3 to 3, excite turbulence with velocity dispersions 100 to 300 km per second, and lift low-entropy gas from cores, preventing catastrophic cooling. Shocks dissipate kinetic energy as heat, with efficiency approximately 1/3 for Mach 2 shocks. Turbulence from jet-driven Kelvin-Helmholtz, Rayleigh-Taylor, and baroclinic instabilities causes mixing and dissipates as heat, providing sustained distributed heating throughout cluster cores. Lifting of low-entropy gas prevents runaway cooling by removing densest gas where cooling would be fastest. This radio mode feedback operates over billions of years, maintaining quasi-equilibrium between heating and cooling. The feedback self-regulates. When cooling increases, gas density increases. More gas accretes onto black hole, accretion rate increases, jet power increases. Additional heating counteracts increased cooling. When cooling decreases, accretion rate decreases, jet power decreases, heating reduces, allowing cooling to increase, restoring balance. This explains the cooling flow problem and demonstrates black holes to regulate thermodynamic state of gas on galaxy and cluster scales. Simulations, including AGN feedback, successfully reproduce observed galaxy properties, including galaxy luminosity function, color magnitude bimodality, and morphology density relation that all fail without AGN feedback. Demonstrating feedback from accreting supermassive black holes is essential. Large cosmological simulations, like Illustris TNG and Eagle, evolve millions of particles across 50 to 300 megaparsec volumes, tracking gravity, hydrodynamics, star formation, stellar feedback, cooling, black hole accretion, and AGN feedback from early universe to present. Without AGN feedback, simulations produce catastrophic failures, too many bright galaxies exceeding observations by factors 3 to 10, too much star formation in massive galaxies, with specific star formation rates remaining high while observations show massive galaxies are quenched, and galaxy colors too blue because star formation continues producing young stars, failing to reproduce observed color bimodality. Including AGN feedback, energy injection, heating gas or momentum from winds and jets dramatically reduces star formation in massive galaxies by heating and expelling gas, successfully reproducing observed luminosity function, color magnitude diagram with red sequence and blue cloud, and morphology density relation. Illustris TNG employs two-mode AGN feedback: thermal quasar mode at high accretion rates, heating surrounding gas, and kinetic jet mode at low rates, driving bipolar relativistic jets. Eagle uses similar approach with stochastic thermal heating proportional to accretion rate. These simulations achieve remarkable agreement with observations, reproducing stellar mass function across redshifts 0 to 8, galaxy sizes and morphologies, quenching in massive galaxies above 10 to the 11th solar masses, color bimodality, and black hole galaxy mass relations consistent with M sigma. Simulations demonstrate AGN feedback is essential. Without it, theory fails. With it, agreement improves dramatically. Main uncertainties involve coupling efficiency of accretion, energy to gas, mode of energy injection, whether thermal or kinetic, geometry, whether isotropic or bipolar, and microphysics of AGN heated gas interactions, including conduction, magnetic fields, turbulence, and multi-phase structure. Despite uncertainties in details, robust result across simulations is that AGN feedback scaling with accretion rate is required to prevent over-efficient star formation and reproduce observed galaxy population. This represents major success of modern astrophysics, understanding how supermassive black holes with tiny mass fractions regulate much larger host galaxies. Testing general relativity, extreme gravity lab. Black holes provide natural laboratories for testing general relativity in the strong field regime, where gravitational effects become large and spacetime curvature approaches maximum values allowed by Einstein's theory. enabling tests in conditions approaching full, non-linear strength of gravity, impossible to achieve elsewhere. Most historical tests of GR operated in weak field limit, where gravitational effects represent small perturbations on flat spacetime. Mercury's perihelion precession advances by 43 arcseconds per century, a 0.012% relativistic correction. Gravitational light deflection deflects starlight by 1.75 arcseconds. Gravitational time dilation on Earth's surface slows time by 1 part in 10 to the 9th. These classical tests beautifully confirm GR in weak field regime, but probe only first-order perturbative corrections to Newtonian gravity. Black holes change this completely. Gravitational waves from mergers and stars orbiting supermassive black holes probe regions where spacetime curvature becomes large and velocities reach substantial fractions of light speed, making relativistic effects dominant rather than night. Corrections. Tests of GR near black holes focus on verifying predictions like frame dragging, absence of monopole gravitational wave radiation, no-hair theorem holding, and absence of deviations from Kerr metric. Frame dragging, or lens-Thirring effect, causes rotating masses to drag spacetime, confirmed by Gravity Probe B, detecting 39 milliarcseconds per year, precession of gyroscopes orbiting Earth, tiny but measurable. Near black holes frame dragging becomes extreme, twisting magnetic fields and enabling jet launching. Gravitational wave observations test whether waves travel at light speed with no dispersion. Any deviation would indicate modifications to GR. All LIGO-Virgo detections show gravitational waves arrive within seconds of electromagnetic counterparts when present and propagate at light speed to within 1 part in 10 to the 15th. Gravitational waves also test polarization. GR predicts spin 2 tensor waves with 2 polarizations, plus and cross, while alternative theories predict additional scalar or vector polarizations. Observations are consistent with GR predictions. The no-hair theorem predicts black holes are characterized completely by mass, spin, and charge, with no additional multipole moments beyond those of Kerr metric, meaning all black holes with same mass and spin are identical regardless of formation history. Alternative theories often predict violations. Scalar tensor theories predict scalar hair. Theories with extra dimensions predict multipole deviations. Some quantum gravity theories predict echoes from horizonless objects. Testing no-hair requires measuring multiple independent properties of same black hole. Gravitational wave observations measure mass and spin from in-spiral waveform plus ring-down quasi-normal mode frequencies if no-hair holds. Measurements from in-spiral and ring-down should agree. Current tests show consistency within errors, but precision is limited. Future observations combining Event Horizon Telescope imaging with gravitational waves will provide more stringent tests. EHT observations of M 87 times and SKR A times constrain deviations from Kerr metric through shadow, shape, and size. Observed shadows match Kerr predictions within 10% uncertainties. Schwarzschild precession causes stellar orbits around black holes to precess rotate their orientation beyond Newtonian predictions. GR predicts orbits precess by angle delta phi approximately 6 pi gm over c squared a times 1 minus e squared per orbit, where a is semi-major axis and e is eccentricity. For star S2 orbiting SKR A times with 16-year period and closest approach 120 AU, precession is approximately 12 arc-minutes per orbit, detectable with current astrometric precision from Keck and VLT telescopes. Observations over multiple orbits have detected this precession at 5 sigma significance, matching GR predictions within uncertainties, ruling out Newtonian gravity and constraining alternative theories. The measured precession is 10 plus or minus 2 arc-minutes per orbit, consistent with GR prediction of 12 arc-minutes. Future observations of closer stars like S62 with 10-year period and S4714 with 12-year period approaching within 100 to 200 AU will measure precession more precisely. S2's pericenter precession also tests parameterized post-Newtonian framework characterizing deviations from GR through parameters like gamma, measuring spacetime curvature, and beta, measuring nonlinearity observations constrain, gamma -1 and beta -1 to less than 0.1. Gravitational redshift measurements from S2 during close passages provide another GR test. As S2 approaches pericenter at 120 AU from SKIA A times, moving at 7,650 km per second, 2.5% light speed, photons climbing out of gravitational well lose energy and redshift by approximately 200 km per second equivalent velocity. Combined with transverse Doppler effect from special relativity adding approximately 100 km per second redshift, total predicted shift is to 300 km per second. Gravity instrument on VLT measured combined gravitational plus transverse Doppler redshift, detecting the shift at high significance, confirming GR predictions and ruling out Newtonian gravity, which predicts no gravitational redshift. These measurements probe gravitational potential phi over c squared approximately 10 to the -4th at S2 pericenter weak field, but stronger than solar system tests. Future extremely close passages by S4714 reaching 12 AU from horizon will probe 100 times stronger fields. Gravitational wave observations test GR in strong field, highly dynamic regime. Binary black hole mergers involve velocities 0.3 to 0.6 c and gravitational potentials GM over RC squared approximately 0.1 to 0.5, fully nonlinear regime inaccessible to perturbative treatments. Observations test propagation speed equaling light speed, absence of dispersion with all frequencies arriving simultaneously, polarization consistent with tensor spin 2 gravitational waves, waveform evolution matching post-Newtonian predictions during in-spiral, merger dynamics matching numerical relativity simulations, and ring-down frequencies matching Kerr, black hole, quasi-normal modes determined by mass and spin. All to 90 detected events show perfect consistency with GR predictions within measurement uncertainties. Residuals after subtracting best-fit GR waveforms show only noise with no systematic deviations. These tests constrain modifications to GR, including varying gravitational constant, extra dimensions, massive gravitons, and alternative theories like scalar tensor or FR gravity, placing limits on deviation parameters at 1 to 10% level. Ring-down tests are particularly powerful for testing no-hair theorem. After merger, perturbed black hole rings at quasi-normal mode frequencies, determined solely by final mass MF and spin AF. The fundamental mode frequency and damping time depend on MF and AF through specific formulas from solving perturbation theory in Kerr spacetime. By measuring fundamental frequency and damping time independently, both MF and AF can be determined. If no hair holds, this measurement should match M, F, and AF determined independently from in-spiral waveform, which encodes mass and spin of progenitors. Current observations show consistency but precision limited by signal to noise. GW 150914 measured MF equals 62 solar masses and AF equals 0.67 from ring down, consistent with spiral-derived values within 20%. Future observations with improved detectors and higher signal-to-noise will test no hair at few percent precision. Alternative theories predicting deviations include dynamical Chern-Simons gravity, predicting spin-dependent modifications, Einstein-Dilaton-Gauss-Bonnet gravity, predicting scalar hair, Ondesky theories predicting modified gravitational wave propagation, and quantum gravity theories predicting Planck scale corrections. Observations constrain these theories. Absence of observed deviations in gravitational wave propagation limits graviton mass to below 10 to the minus 23rd eV. Consistency of ring-down with Kerr predictions limits deviations from no-hair theorem to below 10 to 20%. Agreement between gravitational wave and electromagnetic observations of GW 170817 constrains speed of gravity to equal speed of light to within 1 part in 10 to the 15th. These tests demonstrate GR remains valid in strong field regime near black holes, building confidence in using GR to model extreme astrophysical phenomena. Future observations with increased sensitivity and higher signal-to-noise will continue testing GR's predictions in ever more extreme conditions, searching for subtle deviations that might reveal new physics beyond Einstein's theory. Testing General Relativity Extreme Gravity Lab. Black holes provide natural laboratories for testing general relativity in strong field regime where gravitational effects become large, approaching full strength of Einstein's nonlinear theory. Most solar system tests operate in weak field limit. Mercury's perihelion precession measures tiny relativistic correction to Newtonian gravity. Gravitational waves from mergers and stars orbiting supermassive black holes probe fully nonlinear regime where spacetime curvature becomes large. Tests focus on verifying GR predictions like frame dragging, lack of monopole gravitational wave emission, no-hair theorem holding, and absence of deviations from Kerr metric. Alternatives to GR predict different strong field behavior, including modified dispersion relations for gravitational waves, violations of no-hair theorem through additional multipole moments, and echoes from horizonless compact objects. Current observations show no confirmed deviations from GR, placing stringent constraints on alternative theories. Schwarzschild precession causes stellar orbits to precess rotate their orientation beyond Newtonian predictions when stars orbit close to black holes. GR predicts orbits precessed by angle delta phi approximately 6 pi gm over c squared a times 1 minus e squared per orbit, where a is semi-major axis and e is eccentricity. For star S2, orbiting Skier A times with 16-year period and closest approach 120 AU, precession is approximately 12 arc-minutes per orbit detectable with current astrometric precision. Observations over multiple orbits have detected this precession matching GR predictions within uncertainties, ruling out Newtonian gravity and constraining alternative theories. Future observations of closer stars, like S62 with 10-year period, will measure precession more precisely. Precession tests parameterized post-Newtonian framework, characterizing deviations from GR through parameters like gamma and beta, measuring spacetime curvature and Nordtvedt effect. The no-hair theorem predicts black holes are characterized completely by mass, spin, and charge, with no additional multipole moments beyond those of Kerr metric. Alternative theories often predict violations. Scalar tensor theories predict scalar hair, theories with extra dimensions predict multipole deviations. Testing no-hair requires measuring multiple independent properties of same black hole. Gravitational wave observations measure mass and spin from inspiral waveform and ring-down quasi-normal mode frequencies. If no-hair holds, these measurements should agree. Current tests show consistency within errors, but precision is limited. Event Horizon Telescope observations of M 87 times and SCR A times constrain deviations from Kerr metric through shadow, shape, and size. Future observations combining EHT imaging with gravitational wave detections or pulsar timing will provide more stringent tests. The future of black hole science. Next generation Event Horizon Telescope will create movies of black hole shadows, revealing time-variable accretion and jet launching, providing unprecedented tests of strong field gravity and accretion physics. Current EHT images of M 87 times and Sagittarius A times represent days of data averaged together, showing time-averaged shadow structure. Adding more telescopes, improving sensitivity, and observing at higher frequencies like 345 GHz will enable imaging on timescales of minutes to hours, matching orbital periods at innermost stable orbits. This will reveal dynamics of hotspots orbiting near the event horizon, allowing direct measurement of orbital periods and velocities to test Kepler's laws in extreme gravity. For Sagittarius A*, hotspots should orbit with periods 30 minutes to several hours at velocities 0.3 to 0.6 times light speed, producing dramatic Doppler boosting and dimming, creating characteristic light curves, revealing orbital dynamics. Time-resolved observations will reveal magnetic field structure in jets and how fields thread through the ergosphere, enabling Blandford's-Nayek energy extraction. Movies will show matter spiraling into black holes in real time, jets launching and precessing, and flares from magnetic reconnection events. Coordinating observations with X-ray satellites will connect shadow dynamics to X-ray variability, revealing how corona and jets relate to disk structure. LISA space mission, launching in the 2030 seconds, will detect gravitational waves from supermassive black hole mergers across cosmic history to redshift 20, probing black hole seeds in the early universe and testing general relativity with exquisite precision. LISA's 3 spacecraft, forming a 2.5 million kilometer triangle, will detect millihertz gravitational waves from merging black holes with masses 10,000 to billion solar masses complementing LIGO, which detects stellar mass mergers. These mergers produce years-long signals, allowing parameter estimation with percent-level precision on masses, spins, distance, and sky location. LISA will detect approximately 10 to 100 supermassive black hole mergers per year, measuring black hole mass function and merger rates across cosmic time to constrain formation scenarios. Detecting mergers at redshift 10 to 20 will reveal whether seed black holes formed through direct collapse of primordial gas clouds with masses 10,000 to 100,000 solar masses, through population 3 stellar remnants, or through runaway stellar collisions. LISA will also detect extreme mass ratio in spirals, where stellar mass objects spiral into supermassive black holes over months to years, emitting approximately 100,000 gravitational wave cycles before plunging, mapping space-time geometry near the horizon with exquisite precision. These systems test the Kerr metric by measuring higher-order multipole moments beyond mass and spin, searching for deviations from no-hair theorem predictions at 0.1 to 1%, precision orders of magnitude better than current tests, potentially revealing exotic physics like quantum gravity corrections or extra dimensions. Multi-messenger astronomy, combining gravitational waves, electromagnetic observations, and neutrinos will provide complete pictures of black hole mergers and accretion by observing events through multiple channels, revealing different physical processes. GW170817 neutron star merger demonstrated this power when gravitational waves were followed by gamma-ray burst, optical, infrared kilonova from R-process nucleosynthesis, synthesizing gold and platinum, and radio emission from relativistic outflows. This single event confirmed neutron star mergers produce short gamma-ray bursts, demonstrated heavy element synthesis origins, constrained neutron star equations of state, and measured the Hubble constant through standard siren technique. Future observations may detect electromagnetic counterparts to black hole mergers if gas surrounds binaries, precursor flares from black holes interacting with disk gas, prompt emission from shocks, or afterglows from recoiling merged black holes ejected at thousands of kilometers per second. Neutrinos from accretion disk winds or jets would probe dense regions opaque to photons. Coordinating observations requires rapid alerts distributed globally, triggering electromagnetic follow-up from radio through gamma rays. Future improvements include increased gravitational wave detector sensitivity, expanded electromagnetic survey capabilities with Rubin Observatory LSST, and improved coordination infrastructure. Understanding black holes' ultimate fate through Hawking evaporation and resolving the information paradox remains a fundamental frontier combining quantum gravity, string theory, and quantum information theory. Black holes radiate thermally through the Hawking effect over extraordinarily long timescales, 10 to the 64th years for stellar mass black holes, 10 to the 100th years for supermassive black holes, vastly exceeding the universe's 13.8 billion year age. Whether information falling into black holes escapes through Hawking radiation or is permanently lost remains unresolved, threatening either quantum mechanics unitarity or general relativity's description of smooth horizon crossing. Hawking's 1974 calculation showed radiation is perfectly thermal carrying, no information about infalling matter, meaning information appears lost. Recent progress using AD-CFT correspondence suggests information is preserved through subtle correlations in Hawking radiation. Page curve calculations show entropy initially increases, reaches maximum when half the black hole evaporates, then decreases as entanglement between early and late radiation enables information escape. Resolving the paradox may require revising quantum mechanics, discovering exotic physics at horizons like firewalls contradicting the equivalence principle, or understanding quantum gravity at the singularity. These questions connect to the holographic principle, suggesting spacetime emerges from quantum information theoretic substrate. Black holes, as quantum information processors, inspire research in quantum error correction and entanglement in curved spacetime. The journey through black holes, from stellar deaths to cosmic collisions to galactic giants regulating galaxy evolution to ultimate questions about quantum gravity, reveals the universe at its most extreme, violent, beautiful, and mysterious. Black holes represent the nexus where classical physics breaks down, where matter achieves maximum density, where space-time curvature reaches ultimate limits, and where our understanding faces profound challenges. Future observations with next-generation instruments will continue unveiling black holes' secrets, testing general relativity in ever stronger fields, mapping space-time geometry near horizons, and potentially revealing exotic physics beyond current theories. The next decades promise revolutionary discoveries as black hole astronomy matures into precision science, combining gravitational waves, electromagnetic observations, and theoretical insights. bringing us closer to understanding nature's most enigmatic objects and the fundamental structure of space-time itself.